Hello there, and welcome to Science for Sleep. Tonight, we are going to spend some quiet time thinking about the place we call home. Not the house or apartment you're in right now, not the street outside your window, and not even the planet beneath your feet. Instead, we will slowly turn our attention to something much larger. Something so large that even the idea of it can feel slightly difficult to hold in the mind. The galaxy we live in. The Milky Way. Most of us have seen it, at least in photographs. A long pale band stretching across a dark sky. A soft cloud of countless stars that seems almost like a faint river of light. But the strange thing about the Milky Way is that, even though we live inside it, we have never truly been able to see its full shape. Imagine trying to understand the layout of an enormous forest while standing somewhere among the trees. You might see trunks nearby, branches above you, and perhaps a path winding into the distance. Yet the full structure of the forest, the way it spreads across hills and valleys, remains hidden unless you step far enough away to look back at it from above. For centuries, that has been our situation with the Milky Way. We are inside the forest, and until recently we could only guess what the whole thing might look like. Now, before we wander further into this story, I want to ask you something simple. Where in the world are you listening from tonight? Perhaps you're at home, getting ready for sleep. Maybe the lights are already dimmed and the room is quiet except for the gentle sound of this narration. Or maybe you are listening while travelling, in a different city, a different country, somewhere far away from where you usually fall asleep. Wherever you are, the sky above you is part of the same enormous structure we are about to explore. And that thought alone can feel quietly remarkable. Because every star you might see tonight, every faint glow in the darkness, is part of the same vast galaxy that has surrounded our planet for billions of years. A galaxy that scientists have been trying to map for a very long time. And recently something changed. A new instrument began looking at the sky with a level of patience and detail that astronomers have never had before. Night after night it observes enormous portions of the heavens, gathering information about billions of stars. This telescope is called the Vera Rubin Observatory, and what it has started to reveal is something both familiar and surprising at the same time. A clearer picture of the Milky Way itself, the true shape of the galaxy we live in. But before we move deeper into that discovery, let me gently invite you to do one small thing. If you find this kind of slow exploration relaxing, if these quiet journeys through science help you unwind at the end of the day, then consider supporting the channel by leaving a like or subscribing. It helps more people find these calm corners of curiosity. And now, as we settle into tonight's story, let's begin with a simple idea. For most of human history, the Milky Way was not understood as a galaxy at all. It was simply a mysterious glow in the sky. Ancient observers noticed it stretching across the darkness like a pale road made of light. Different cultures described it in different ways. Some imagined it as a heavenly river. Others thought it was the path of spirits, or the trail of some cosmic creature moving across the night. None of those explanations were meant to be scientific in the modern sense. They were attempts to describe something beautiful and puzzling using the knowledge available at the time, and for thousands of years that faint band of light remained exactly that, a mystery. Even when early telescopes were invented in the 1600s, the situation did not immediately become clearer. Those instruments revealed something important though. When astronomers pointed their telescopes toward the Milky Way, they noticed that the pale glow was not actually a cloud. It was made of stars, an enormous number of stars. So many, in fact, that they blended together into a soft band of light when seen from Earth. This realization slowly changed the way people thought about the night sky. Instead of imagining the Milky Way as a luminous mist, scientists began to understand that it might be a vast collection of stars spread across space. But even then, the bigger picture was still hidden. How big was this collection of stars? What shape did it form? And where exactly were we located inside it? Those questions would occupy astronomers for centuries. During the late 19th and early 20th centuries, researchers began attempting something very ambitious. they tried to map the Milky Way. Using telescopes, careful measurements, and a great deal of patience, they counted stars in different directions across the sky. By estimating how far away those stars were, they hoped to piece together the structure of the galaxy itself. At first, the results seemed promising. One astronomer named Jacobus Kapteyn proposed that the Milky Way might be shaped like a flattened disk of stars, somewhat similar to a giant spinning plate. According to his calculations, our Sun appeared to sit close to the centre of this disk. For a while, that idea seemed reasonable, but it turned out to be incomplete. The problem was something that astronomers had not fully accounted for yet: cosmic dust. Between the stars scattered throughout the galaxy, there are enormous clouds of fine particles. These clouds absorb and scatter light, making distant stars appear dimmer than they really are. To an observer trying to measure the structure of the Milky Way, that dust acts like a fog. It hides large portions of the galaxy from view. So when early astronomers counted stars, they were unknowingly missing many of them. Entire regions of the Milky Way remained invisible behind thick curtains of interstellar dust. As telescopes improved and new methods of measurement were developed, scientists gradually realized that the galaxy was much larger than those early maps suggested, and our position inside it was not near the center at all. Instead, the solar system sits far out in one of the galaxy's spiral arms, orbiting the center along with hundreds of billions of other stars. Even today, mapping the Milky Way remains one of the most difficult tasks in astronomy. And the reason is surprisingly simple. We are still inside the forest, trying to understand the structure of something as vast as a galaxy, while standing within it is incredibly challenging. We cannot step outside the Milky Way to take a photograph from afar. Everything we know must be reconstructed from the inside. Astronomers study the motions of stars, measure their distances, analyze the distribution of gas and dust, and combine enormous data sets gathered by telescopes around the world. Each piece of information adds another small fragment to the puzzle. Yet for many decades, the overall picture remained uncertain. Different models suggested different numbers of spiral arms. Some maps showed the galaxy as relatively smooth and symmetrical, while others hinted at a more irregular structure. It was clear that we were missing something. What scientists needed was a way to observe enormous numbers of stars over long periods of time, tracking how the galaxy changes and evolves. They needed a telescope that could watch the sky continuously, gathering an unprecedented amount of data. And that is exactly what the Vera Rubin Observatory was designed to do. High in the mountains of Chile, far from the glow of city lights, this remarkable instrument began preparing for a new kind of sky survey. Instead of focusing on one small patch of the heavens at a time, it would scan vast areas repeatedly, night after night, building a dynamic map of the universe. Its camera alone is one of the largest ever built for astronomy, capable of capturing incredibly detailed images of huge sections of the sky. With that capability, astronomers can observe billions of stars and track their subtle motions over time. And slowly, almost quietly, patterns begin to emerge. Patterns that reveal how the Milky Way is structured. Patterns that help scientists trace the spiral arms of our galaxy with far greater clarity than before. Patterns that may finally show us the true shape of the enormous stellar system we call home. But understanding those patterns requires looking at the sky in a completely different way. Instead of taking a single snapshot of the cosmos, astronomers must watch it like a long unfolding story, observing how stars move, how their brightness changes, and how entire regions of the galaxy shift over time. That approach is what makes the Rubin Observatory so powerful. It does not simply photograph the sky, it studies how the sky evolves. And as those observations accumulate, the map of the Milky Way slowly becomes more detailed, more accurate, and more surprising than anything scientists previously imagined. Because the galaxy we live in is not just a simple spiral disk of stars. It bends, it warps. It contains streams of ancient stars left behind by long-forgotten galactic collisions. And in ways that astronomers are only now beginning to understand, the Milky Way continues to change even today. But to appreciate how remarkable this new view of our galaxy truly is, we first need to spend a little time thinking about the strange challenge of trying to understand a structure while living inside it. For a very long time, the Milky Way felt familiar to us in a quiet and almost comforting way. It was always there, night after night, long before cities filled the horizon with electric light. People could simply step outside, look upward, and see that pale band stretching across the darkness. A wide, faint glow scattered with countless tiny points of light, forming a soft river that seemed to flow across the sky. To ancient observers, it did not look like a distant object at all. It looked like part of the sky itself, almost like a texture woven into the darkness above. Because of that, early explanations for the Milky Way were often imaginative rather than scientific. Different civilizations gave it names, stories, and meanings that reflected their cultures. In ancient Greece, the pale glow was connected to mythology. According to one story, the Milky Way was formed when the goddess Hera spilled divine milk across the heavens. The Greek word galaxius, which later gave us the word galaxy, actually comes from the word for milk. Other cultures saw different images. In parts of Asia, the Milky Way was sometimes imagined as a celestial river separating lovers who could only meet once a year. In many indigenous traditions around the world, the glowing band represented pathways, animal spirits, or the trails of ancestors crossing the sky. None of these explanations attempted to measure the structure of the universe. They were ways of describing something mysterious using stories and symbolism, and that mystery remained intact for thousands of years. Even the earliest astronomers, who carefully tracked the movements of the sun, moon, and planets, could not easily explain what the Milky Way actually was. It looked different from every other object in the sky. Stars appeared as distinct points of light. Planets wandered slowly against the background of those stars, but the Milky Way looked like a faint cloud. A cloud that never moved, a cloud that stretched from one horizon to the other. For centuries, no one had the tools to look closely enough to see what it was made of. Then, in the early 1600s, something changed. A new invention began to spread across Europe, a simple instrument made of lenses that could magnify distant objects, the telescope. When Galileo Galilei turned his telescope toward the Milky Way in 1610, he made a discovery that would permanently change humanity's understanding of the night sky. The glowing band was not a cloud at all. Instead, it was composed of an enormous number of individual stars. So many stars, in fact, that their light blended together when viewed with the naked eye. Galileo wrote about this in his observations, describing how the Milky Way was filled with countless faint stars that had never been visible before. His telescope revealed that the universe was far richer and more crowded than anyone had imagined. That realization was both exciting and confusing at the same time. If the Milky Way was made of stars, then what exactly was it? Was it a cluster of stars surrounding our solar system? Was it the entire universe? Or was it only one part of something much larger? At that time, no one could answer those questions with confidence. For the next few centuries, astronomers slowly improved their instruments and observations. Telescopes became larger. Optical technology advanced. Scientists began carefully cataloguing stars and studying their brightness and positions. As more data accumulated, a general idea started to emerge. The Milky Way might be shaped like a flattened disk of stars. That idea came from noticing how the stars in the sky are distributed. If you look upward on a very dark night far away from city lights, you may notice that stars appear more densely packed along the band of the Milky Way itself. In other directions, away from that band, the sky looks less crowded. This pattern suggested something important. If the galaxy was shaped like a disk, and if we were located somewhere inside that disk, then looking along the plane of the disk would reveal many more stars than looking upward or downward away from it. That explanation made sense. However, knowing that the galaxy might be a disk did not immediately tell astronomers how big it was, or where exactly our solar system was located inside it. To figure that out, scientists needed a way to measure the distances to stars, and measuring distances across space is surprisingly difficult. Nearby objects can be measured using a method called parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring that tiny shift, astronomers can calculate how far away those stars are. But parallax works best for relatively nearby stars. As distances increase, the shifts become too small to measure easily. So astronomers developed other techniques. They studied stars with known brightness, using them as standard candles. If you know how bright a star truly is, you can estimate its distance by comparing that intrinsic brightness to how dim it appears from Earth. With these methods, scientists began attempting something ambitious during the late 19th and early 20th centuries. They tried to map the Milky Way. One of the most influential figures in this effort was a Dutch astronomer named Jacobus Kapteyn. Around the early 1900s, Kapteyn organised an enormous project involving astronomers around the world. Together they counted stars in many different directions across the sky and estimated their distances. Using this data, Kapteyn created one of the first models of the Milky Way's structure. According to his calculations, the galaxy appeared to be shaped like a flattened disk about 50,000 light-years across. In this model, the Sun was located relatively close to the centre. At the time, this seemed like a remarkable achievement. For the first time in history, humans had a rough map of the galaxy they lived in. But there was a problem hidden inside those calculations, a problem that no one fully recognised at first. The Milky Way contains enormous clouds of dust and gas between its stars. These clouds absorb and scatter light, especially the shorter wavelengths of visible light that our eyes detect. In effect, they act like cosmic fog. When astronomers look through these dusty regions, distant stars appear dimmer than they actually are. Some stars become completely invisible. Because Kapteyn and his colleagues did not fully account for this dust, their map underestimated the true size of the Milky Way. Large portions of the galaxy were hidden behind these clouds. Another astronomer, Harlow Shapley, later approached the problem from a different angle. Instead of focusing mainly on individual stars, Shapley studied globular clusters. Globular clusters are dense spherical groups of stars that orbit the Milky Way. Each cluster contains hundreds of thousands, sometimes millions, of stars bound together by gravity. By measuring the distances to many globular clusters, Shapley noticed something interesting. These clusters were not distributed evenly around the Sun. Instead, they formed a roughly spherical cloud that seemed to be centered in a particular direction in the sky, toward the constellation Sagittarius. From this pattern, Shapley concluded that the true center of the Milky Way must lie far away in that direction, not near our solar system. In his model, the galaxy was much larger than Kapteyn's earlier estimate, and the Sun occupied a position far from the center. This was an important shift in perspective. For centuries, humanity had often imagined itself near the center of the universe. First, Earth was thought to be the center of everything. Later, even when the Sun replaced Earth in the center of the solar system, it was still tempting to think that our star might sit at the center of the galaxy. Shapley's work suggested otherwise. We were not in the middle of the Milky Way at all. We were somewhere out toward the edges. Over time, further observation supported this conclusion. The center of the galaxy lies tens of thousands of light-years away from us, hidden behind thick clouds of dust in the direction of Sagittarius. Today we know that a supermassive black hole resides there, surrounded by dense clusters of stars. Meanwhile, our solar system quietly orbits that center, along with hundreds of billions of other stars. Even with this improved understanding, the Milky Way still held many secrets. Astronomers began noticing hints that the galaxy might have spiral arms, similar to those seen in distant galaxies observed through powerful telescopes. When scientists looked outward into the universe, they could see beautiful spiral galaxies with winding arms of stars and gas. It seemed reasonable that our own galaxy might share a similar structure. But confirming that idea was extremely difficult. Remember the forest analogy from earlier? If you stand deep within a forest, surrounded by trees in every direction, it becomes very hard to determine the overall pattern of the forest itself. Are the trees arranged in rows? Are they clustered on hillsides? Does the forest stretch farther in one direction than another? From inside, your view is limited. That is exactly the challenge astronomers face when trying to map the Milky Way. We cannot step outside our galaxy to take a photograph. Instead, we must infer its structure indirectly by studying the stars around us. Over the past century, scientists used radio telescopes to observe clouds of hydrogen gas throughout the galaxy. Radio waves can pass through dust more easily than visible light, allowing astronomers to detect structures that would otherwise remain hidden. These observations revealed large spiral patterns in the distribution of gas in star-forming regions. Gradually, astronomers pieced together a rough picture of the Milky Way as a barred spiral galaxy. This means the central region contains a bar-shaped structure of stars with spiral arms extending outward from its ends. Yet even this model remained uncertain. Different studies suggested different numbers of spiral arms. Some maps showed 4 main arms. Others suggested that 2 major arms might dominate the structure. The exact shape was still debated, and that uncertainty persisted for decades. Even today, if you search for illustrations of the Milky Way, you may notice that many of them are slightly different. Some diagrams emphasize certain arms more than others. Some show additional smaller arms branching outward. These variations exist because astronomers have been working with incomplete information. The galaxy is enormous, roughly 100,000 light-years across and filled with dust, gas, stars, and dark matter. Mapping every part of it requires observing vast numbers of objects across enormous distances. Until recently, collecting that much data simply was not possible. But astronomy has entered a new era. Modern telescopes equipped with advanced digital detectors can observe millions or even billions of stars. Space missions like Gaia have measured the positions and motions of stars with extraordinary precision, and now the Vera Rubin Observatory is preparing to contribute something even more remarkable. Instead of focusing on individual regions of the sky, it will repeatedly scan huge portions of the heavens, building an evolving map of the universe over time. With that approach, astronomers will be able to track how stars move within the Milky Way, how stellar streams arc through space, and how different regions of the galaxy connect to one another. Those observations are beginning to reveal a much more detailed and dynamic picture of our cosmic home. A picture that may finally answer one of the oldest questions in astronomy. What does the Milky Way actually look like? But before those discoveries fully unfold, it helps to pause and remember something quietly remarkable. For thousands of years, humans could only look at that pale river of light in the night sky and wonder what it was. Today, we're beginning to understand the enormous structure hidden within it. Trying to understand the Milky Way from inside it is a little like trying to understand the shape of a city while standing somewhere on one of its streets. Imagine walking through a large city at night. Buildings rise around you, lights stretch down long avenues, cars pass by, and the streets twist and turn as they continue into the distance. From where you stand, you might be able to see the nearby blocks clearly. You could recognize individual buildings, intersections, and perhaps even the skyline in one direction. But the full layout of the city would still remain hidden. You would not easily know where every neighborhood sits. You would not immediately see how the roads connect across the entire landscape. And you certainly would not be able to understand the overall shape of the city just by looking down a single street. To see that bigger picture, you would need to rise high above the ground. A satellite photograph would help. A view from an airplane might help, something that allows you to step far enough away from the streets to observe the entire pattern at once. But when it comes to the Milky Way, astronomers do not have that option. We cannot leave the galaxy and look back at it from the outside. No spacecraft has ever travelled even a tiny fraction of the distance required to see the Milky Way from beyond its borders. In fact, the most distant spacecraft humanity has launched, the Voyager probes, have only recently begun entering the outermost region of our solar system. Compared to the size of the galaxy, that distance is still incredibly small. The Milky Way stretches roughly 100,000 light-years across. Voyager 1, travelling faster than any other human-made object, would need tens of millions of years to reach the far side of the galaxy. So when astronomers attempt to understand the shape of the Milky Way, they must do something far more subtle. They must reconstruct the map from the inside. This is not a straightforward process. Every star we see from Earth is just one point in a vast three-dimensional structure. Some stars are close, others are hundreds or thousands of light-years away. Still others lie so far across the galaxy that their light has been travelling toward us since before humans existed as a species. When we look up at the sky, all of those stars appear projected onto a two-dimensional surface. It is almost like looking at a photograph where objects at many different distances overlap each other. That makes it difficult to tell which stars are actually near one another in space. Consider a simple example. If you look toward the constellation Orion, you might see several bright stars forming a recognizable pattern. To our eyes, they appear as though they belong to the same group, perhaps even sitting near one another. But in reality, those stars are separated by enormous distances. Some are a few hundred light-years away, others lie much farther beyond. They only appear close together because they happen to line up along the same direction from our viewpoint on Earth. This effect becomes even more complicated when we try to study the structure of an entire galaxy. When astronomers observe the Milky Way, they are essentially looking through a crowded field of stars that stretch across thousands of light-years in every direction. The stars overlap in our line of sight, making the galaxy appear like a dense wall of light. Untangling that wall requires careful measurement. Scientists must determine how far away each star is. They must measure how stars move through space. They must also account for the effects of interstellar dust, which can hide entire regions of the galaxy from view. All of these challenges combine into one of the most complex mapping problems in astronomy. And yet, astronomers have been slowly solving it. The first step in understanding the Milky Way from the inside involves measuring stellar distances as accurately as possible. Without distance measurements, the map cannot even begin to form. Earlier, we briefly mentioned the method called parallax. This technique works because Earth moves around the Sun once every year. As our planet travels along its orbit, nearby stars appear to shift slightly against the background of more distant stars. The shift is extremely small, often measured in tiny fractions of a degree, but with precise instruments it can be detected. By measuring this tiny change in position, astronomers can calculate the distance to the star. Parallax works very well for stars relatively close to our solar system. However, beyond a certain distance, the shift becomes too small to detect with traditional telescopes. For much of the 20th century, this limited the size of the region that astronomers could map accurately. Fortunately, modern space telescopes have changed that. One of the most important missions in this effort is the European Space Agency's Gaia spacecraft. Gaia has been measuring the positions and motions of more than 1 billion stars in the Milky Way with extraordinary precision. For many of those stars, Gaia can determine distance using parallax measurements, far more accurate than anything previously possible. This has allowed astronomers to build a three-dimensional map of a large portion of our galaxy. Instead of simply seeing stars projected onto the sky, scientists can now estimate their positions within the Milky Way's disk. But even Gaia cannot see everything. Large clouds of interstellar dust still block visible light in many regions of the galaxy. These dusty areas appear as dark patches when astronomers observe the Milky Way with optical telescopes. If you have ever looked closely at photographs of the Milky Way, you may have noticed dark lanes cutting through the bright band of stars. Those lanes are caused by dense clouds of dust absorbing the light behind them. To peer through those regions, astronomers often use other wavelengths of light. Radio waves, for example, can travel through dust much more easily than visible light. By observing radio emissions from hydrogen gas, scientists can trace the large-scale structure of the galaxy even in places where stars are hidden. Infrared observations also help. Infrared light penetrates dust more effectively, allowing telescopes to detect stars that would otherwise remain invisible. By combining observations across multiple wavelengths, astronomers gradually assemble a clearer picture of the Milky Way structure. Still, another challenge remains. The galaxy is not static. Stars move. Each star in the Milky Way orbits the center of the galaxy under the influence of gravity. Our own Sun, along with its planets, travels around the galactic center at a speed of roughly 220 kilometers per second. At that speed, the solar system completes one full orbit every 225 to 250 million years. Astronomers sometimes refer to this as a galactic year. While stars follow these enormous orbits, they also move slightly relative to one another. Over millions of years, clusters of stars spread apart. Streams of stars drift through the galaxy after gravitational encounters. All of this motion means that the map of the Milky Way is constantly evolving. If someone could observe the galaxy over tens of millions of years, they would see its structure shifting slowly, almost like a cosmic dance unfolding across space. Tracking those movements provides valuable information about how the galaxy is organized. For example, groups of stars that share similar motions may have formed together in the same region long ago. Other stars may have been pulled into the Milky Way during ancient collisions with smaller galaxies. By studying stellar motions, astronomers can uncover clues about the galaxy's history. This approach requires enormous data sets. Instead of observing a few thousand stars, scientists now analyze millions or billions of them, searching for patterns in their positions and velocities. That is where modern survey telescopes become incredibly important. A telescope that can observe large portions of the sky repeatedly over many years can track how stars change position and brightness. Those observations provide the raw data needed to build detailed maps of the galaxy. The Vera Rubin Observatory is designed specifically for this kind of work. Its main project, known as the Legacy Survey of Space and Time, will photograph the entire visible sky every few nights. Over the course of a decade, it will collect tens of millions of images. Each image will capture countless stars, galaxies, and other objects. When those images are combined, astronomers will be able to measure subtle changes in the positions of stars across time. Even tiny motions that were previously impossible to detect may become visible. In effect, the Rubin Observatory will allow scientists to watch the Milky Way move. This continuous observation is essential for understanding the galaxy from the inside. Instead of trying to infer the structure from a single snapshot, astronomers can observe how stars drift through space, revealing the gravitational patterns that shape the galaxy. Those patterns can outline spiral arms, stellar streams, and other structures that are otherwise difficult to see. The process is somewhat similar to studying the flow of water in a river. If you look at a river for only a moment, you might see ripples and reflections but struggle to understand the overall direction of the current. However, if you watch the river for a long time, you begin to notice how leaves, bubbles, and small objects move with the flow. Gradually, the direction of the current becomes clear. In a similar way, watching the motions of stars over time reveals the hidden structure of the Milky Way. But there is still something else that makes mapping our galaxy especially fascinating. Because when we build this map, we are also discovering our own location within it. The solar system sits about 26,000 light-years from the galactic center. We reside in a region known as the Orion Arm, sometimes called the Orion Spur. This is a smaller spiral arm located between two larger ones, the Sagittarius Arm and the Perseus Arm. From our position here, we look inward toward the crowded central regions of the galaxy and outward toward the quieter outskirts. Both directions contain enormous numbers of stars. When you step outside on a very dark night and see the Milky Way stretching across the sky, you are looking along the plane of this enormous disk. In that direction, Your line of sight passes through thousands of light-years of stars, gas, and dust. That is why the Milky Way appears as a bright band rather than a scattered field of stars. You're looking through the thickest part of the galaxy, yet even that view only hints at the true scale of what surrounds us. Beyond the visible stars lie vast clouds of gas where new stars are forming. Beyond those clouds stretch additional spiral arms. Surrounding the entire disk is a halo of older stars and mysterious dark matter that extends far beyond the galaxy's visible edges. All of this structure exists around us at this very moment, and until recently much of it remained hidden within incomplete maps and uncertain models. But as new telescopes continue to observe the sky with greater precision, the map is slowly becoming clearer. We are beginning to see not only where the stars are located, but how they move together as part of a much larger system. And as that map improves, one particular instrument is starting to play a crucial role in revealing the deeper structure of our galaxy. An observatory built to watch the sky continuously, patiently collecting the data needed to understand the Milky Way in ways that were never possible before. Once astronomers realized that the Milky Way was far larger and more complex than early maps suggested, the effort to understand its structure entered a long and careful phase. This was not the kind of discovery that happens overnight. Instead, it became a slow investigation that stretched across decades, involving many scientists, many telescopes, and many different ways of looking at the sky. The challenge was simple to describe but extremely difficult to solve. If the Milky Way is a vast disk of stars with spiral arms, then where exactly are those arms located, and how many of them are there? Astronomers suspected that our galaxy might resemble other spiral galaxies observed in distant parts of the universe. When powerful telescopes captured images of galaxies millions of light-years away, scientists could clearly see their structure. Many of them displayed elegant spiral patterns, with bright arms of stars winding outward from a central region. Some galaxies showed 2 major spiral arms, others had 4 or more. In many cases, the arms contained bright clusters of young stars and glowing clouds of gas where new stars were forming. These spiral galaxies were beautiful and surprisingly common. It seemed reasonable that the Milky Way might have a similar structure. However, confirming that idea from inside the galaxy proved extremely difficult. Looking outward toward distant galaxies is in some ways easier than studying our own. When astronomers observe another galaxy millions of light-years away, they can see the entire object at once, much like looking at a photograph. But when we study the Milky Way, we are embedded within it. We cannot see its overall shape directly. Instead, scientists must gather information from countless stars scattered across the sky and attempt to assemble those pieces into a larger picture. During the early and mid-20th century, astronomers began focusing on objects that could help reveal the locations of spiral arms. One of the most useful clues came from regions where new stars are forming. Stars are born inside large clouds of gas and dust known as nebulae. These stellar nurseries glow brightly because young, hot stars illuminate the surrounding gas. When astronomers observe these regions, they can identify areas where star formation is actively occurring. If spiral arms exist within the Milky Way, they should contain many of these star-forming regions. By mapping the positions of nebulae and young star clusters, astronomers hope to trace the outlines of the galaxy's spiral pattern. But again, the problem of distance made this work difficult. Knowing the direction of a nebula in the sky was not enough. Scientists also needed to determine how far away it was. Without that information, it was impossible to place the object accurately within the galaxy. To solve this, astronomers developed additional methods for estimating distances. Certain types of stars change brightness in predictable ways. These stars, known as variable stars, can act as cosmic measuring tools. One famous example is the Cepheid variable. These stars pulsate, expanding and contracting over time. The period of their pulsation is directly related to their true brightness. By measuring how quickly a Cepheid variable changes brightness, astronomers can determine how luminous it really is. Comparing that intrinsic brightness to how bright the star appears from Earth allows scientists to estimate its distance. This technique proved extremely valuable. Cepheid variables were discovered in many regions of the Milky Way, including star clusters and nebulae associated with spiral arms. By measuring their distances, astronomers could begin placing these structures within a three-dimensional map of the galaxy. Gradually, patterns started to appear. Some regions of star formation seemed to align along long arcs across the galaxy. These arcs hinted at the presence of spiral arms, though the exact details remained uncertain. Around the same time, another powerful tool entered the search: radio astronomy. Unlike visible light, radio waves can pass through clouds of dust without being absorbed. This allowed astronomers to observe regions of the galaxy that optical telescopes could not see clearly. One of the most important discoveries in radio astronomy involved hydrogen gas. Hydrogen is the most abundant element in the universe, and it emits radio waves at a very specific wavelength known as the 21 centimeter line. By observing this emission, scientists can detect large clouds of hydrogen spread throughout the Milky Way. These clouds often trace the structure of spiral arms. Using radio telescopes, astronomers began mapping the distribution of hydrogen gas across the galaxy. By measuring how the wavelength of the radio emission shifted due to the Doppler effect, they could also estimate how these clouds were moving relative to Earth. This information provided clues about their positions within the galaxy. When scientists combined these radio observations with optical measurements of stars and nebulae, a more detailed picture of the Milky Way started to emerge. The galaxy appeared to contain multiple spiral arms extending outward from a central region. However, the exact number and arrangement of these arms remained uncertain. Some models suggested that the Milky Way had 4 major spiral arms, similar to certain galaxies observed elsewhere in the universe. Other studies indicated that 2 dominant arms might exist, with smaller secondary arms branching between them. The difficulty came from the fact that different methods of observation sometimes produce slightly different results. Radio observations might suggest one pattern of gas clouds. Optical observations of stars might suggest another. Infrared observations might reveal additional structures hidden behind dust. Piecing these data sets together was like assembling a puzzle with many missing pieces. Meanwhile, astronomers also began discovering something else about the Milky Way. It was not perfectly flat. The disk of the galaxy, which contains most of its stars, gas and dust, appears to bend slightly at large distances from the centre. This bending is known as the galactic warp. Imagine a vinyl record that has been gently warped so that its outer edges curve slightly above and below the central plane. Something similar appears to happen in the Milky Way. Observations of hydrogen gas in the outer regions of the galaxy revealed that the disk gradually twists and bends as it extends outward. The exact cause of this warp is still studied today, but it may be influenced by gravitational interactions with nearby satellite galaxies, or the distribution of dark matter surrounding the Milky Way. These discoveries made the map of our galaxy even more complex. Instead of a perfectly symmetrical spiral disk, the Milky Way appeared to be a dynamic structure with irregular features. Astronomers also began noticing streams of stars moving together through the galaxy. These stellar streams often represent the remnants of smaller galaxies that were pulled apart by the Milky Way's gravity long ago. As those smaller galaxies merged with the Milky Way, their stars were stretched into long arcs that continue orbiting the galactic center. Finding and mapping these streams provides valuable information about the galaxy's past. They act like fossil traces of ancient cosmic events. By the late 20th century, the overall picture of the Milky Way had improved significantly compared to earlier centuries. Astronomers were confident that the galaxy contained hundreds of billions of stars arranged within a rotating disk. They knew that the solar system orbited the galactic center far from the middle. They had evidence of spiral arms, a central bulge of stars, and a halo of older stars surrounding the disk. But despite all of this progress, the map was still incomplete. Many regions of the galaxy remained poorly understood. The exact structure of the spiral arms was still debated. The distribution of stars in the outer disk was uncertain. Even the total size of the Milky Way remained difficult to measure precisely. The reason for this lingering uncertainty was not a lack of effort. Astronomers had spent generations studying the galaxy with every tool available to them. The real limitation was the amount of data. Earlier surveys could only observe relatively small portions of the sky at a time. Even large projects often focused on specific regions rather than the entire galaxy. To fully understand the Milky Way structure, scientists needed a telescope capable of observing enormous numbers of stars repeatedly across the entire sky. They needed a way to collect vast data sets over many years, tracking how stars move and how different regions of the galaxy change over time. That kind of project required new technology. It required extremely sensitive digital detectors capable of capturing huge images of the sky. It required powerful computers to process enormous volumes of data, and it required a telescope designed specifically for large-scale sky surveys. For a long time, such an instrument existed mostly as an idea. Astronomers knew that if they could build a telescope capable of observing the entire sky every few nights, they could track the positions and motions of billions of stars. With that information, the structure of the Milky Way might finally become much clearer. The galaxy's spiral arms could be traced with greater accuracy. Stellar streams could be mapped in detail. Subtle motions of stars might reveal the gravitational influence of dark matter surrounding the galaxy. Eventually, that idea became reality. In the mountains of northern Chile, construction began on an observatory designed to observe the sky in exactly this way. It would use one of the largest digital cameras ever built for astronomy. Its mission would be to photograph huge portions of the sky repeatedly for an entire decade, collecting an unprecedented amount of information about stars, galaxies, and other objects. This facility would later be named the Vera Rubin Observatory, and the data it gathers is expected to transform our understanding of the Milky Way, because after more than a century of searching, astronomers are finally gaining the tools needed to study our galaxy with the level of detail it deserves. The long search for the Milky Way's true structure is still continuing. But now, for the first time, scientists are beginning to see the possibility of a much clearer answer. And that answer may emerge not from a single observation, but from patiently watching the sky night after night as new data slowly reveals patterns hidden within the enormous stellar system we call home. Even after astronomers began building better maps of the Milky Way, another problem continued to slow their progress. It was not a problem with the telescopes themselves. It was not a lack of effort or curiosity. Instead, the obstacle was something spread quietly throughout the galaxy itself: dust. When we hear the word dust, it might sound insignificant. On Earth, dust is something we wipe off a shelf or notice floating in a beam of sunlight. It seems small and unimportant. But in space, dust can shape what we are able to see across enormous distances. Between the stars of the Milky Way, there are vast clouds of gas and tiny solid particles. These particles are extremely small, often smaller than grains of smoke, and they are made of materials like carbon, silicates, and ice. Although each individual particle is microscopic, the combined effect of trillions upon trillions of them can become powerful. When starlight travels through these clouds, some of that light is absorbed and scattered. The result is similar to what happens on a foggy evening here on Earth. Imagine standing on a road during a thick fog. Streetlights may still glow in the distance, but their light appears dimmer and more diffuse. Objects far away gradually disappear as the fog thickens. In space, interstellar dust acts in a very similar way. Astronomers often describe this effect as cosmic fog. It spreads across large regions of the Milky Way, blocking and distorting the light from distant stars. If you look closely at photographs of the Milky Way taken from very dark locations on Earth, you might notice dark streaks cutting through the bright band of stars. These streaks are not empty space. They are actually dense clouds of dust. that prevent light from stars behind them from reaching us. Some of these dust clouds stretch across hundreds of light years. Others are even larger. Because of this cosmic fog, large portions of our galaxy remain hidden when we observe the sky using visible light. It is not that the stars are absent, it is simply that their light cannot pass easily through the dust. For astronomers trying to map the Milky Way, this creates a serious challenge. Imagine trying to map an entire city while thick fog covers half the streets. You might see certain neighborhoods clearly, while others remain completely obscured. From your perspective, those hidden areas might appear empty, even though they are actually full of buildings and activity. That is exactly the kind of confusion dust creates in the Milky Way. Early astronomers who counted stars across the sky often underestimated how many stars existed in distant regions of the galaxy. The dust dimmed their light so much that many of them became invisible to telescopes. As a result, the early maps of the Milky Way suggested a galaxy smaller than it truly is. This realization slowly emerged during the 20th century, as astronomers began studying how dust affects starlight. One of the clues involved colour. Dust does not block all wavelengths of light equally. Shorter wavelengths, such as blue light, are scattered more easily than longer wavelengths like red light. Because of this effect, stars that lie behind dust clouds often appear redder than they actually are. The dust removes some of the blue light, allowing more of the red light to pass through. Astronomers call this phenomenon interstellar reddening. By studying how much a star's light has been reddened, scientists can estimate how much dust lies between us and that star. This information helps them correct their distance measurements and better understand the distribution of dust throughout the galaxy. Even with these corrections, however, dust still limits how far we can see using ordinary optical telescopes. To overcome this obstacle, astronomers began exploring other parts of the electromagnetic spectrum. Light comes in many forms beyond the visible colours our eyes can detect. Radio waves, infrared radiation, ultraviolet light, and X-rays are all part of the same spectrum of electromagnetic energy. Some of these wavelengths travel through dust much more easily than visible light. Infrared light, for example, can pass through many dusty regions that would completely block optical observations. By observing the Milky Way in infrared wavelengths, astronomers can detect stars that would otherwise remain hidden. This approach has revealed enormous numbers of stars in the central regions of the galaxy. The galactic centre lies in the direction of the constellation Sagittarius, but thick clouds of dust obscure it when viewed with visible light. Infrared telescopes, however, can penetrate those clouds and observe the dense clusters of stars surrounding the centre. Radio astronomy has also played a crucial role. As mentioned earlier, hydrogen gas emits radio waves at a specific wavelength of about 21 centimeters. These radio waves pass through dust almost completely unaffected. Using radio telescopes, astronomers have been able to trace huge clouds of hydrogen gas across the Milky Way. These observations reveal structures that optical telescopes cannot see. Many of those hydrogen clouds outline the spiral arms of the galaxy. In other words, even though dust hides parts of the Milky Way from our eyes, radio waves allow scientists to detect the large-scale structure of the galaxy. Still, dust is not the only obstacle in mapping the Milky Way. Distance itself creates another layer of difficulty. The galaxy is unimaginably large. Even the nearest stars beyond our solar system are several light years away. As distances increase to thousands or tens of thousands of light years, measuring them becomes extremely challenging. When astronomers look toward the central regions of the Milky Way, they are observing stars whose light began travelling toward Earth long before recorded history. Some of those stars are so far away that their distances must be estimated indirectly through careful statistical methods. And as distances grow larger, the uncertainties also grow. This combination of dust and distance means that the Milky Way cannot be mapped as easily as nearby star clusters or distant galaxies. Nearby star clusters can often be observed clearly because they occupy a relatively small region of space. Distant galaxies can sometimes be photographed in their entirety because they are far enough away that their full structure fits into a single field of view. But the Milky Way sits in an awkward middle ground. It is too large for us to see all at once, and we are too deep inside it to step outside and look back. So astronomers must rely on enormous surveys of stars across the sky. They gather distance measurements, track stellar motions, analyze the distribution of gas and dust, and combine all of this information into detailed models of the galaxy's structure. This process is slow and methodical. Each new survey adds more data. Each new telescope reveals another piece of the puzzle. Over time, those pieces begin to form a clearer picture. Yet even today, the cosmic fog of dust still hides important details. Certain spiral arms remain difficult to trace. Some regions of star formation are only partially understood. The outer edges of the Milky Way's disk are still being explored. But modern astronomy is steadily pushing through that fog. Space telescopes equipped with infrared detectors are mapping stars in dusty regions with unprecedented sensitivity. Radio observatories are tracing gas clouds across vast distances. Meanwhile, large sky surveys are measuring the positions and motions of millions and eventually billions of stars. The Vera Rubin Observatory will contribute to this effort in a unique way. While it primarily observes visible light, its enormous field of view and repeated observations of the sky will allow astronomers to track changes in brightness and motion for vast numbers of stars. Even stars partially hidden behind dust may become detectable through careful analysis of repeated observations. By combining Rubin's data with infrared and radio surveys, scientists can build much more complete maps of the Milky Way. Each dataset acts like a different layer of vision. Visible light shows us many of the stars themselves. Infrared light reveals stars hidden behind dust. Radio observations trace the clouds of gas where new stars are forming. When these layers are combined, the galaxy becomes far easier to understand. But there is still another complication in this story. Because the Milky Way is not just a collection of stars sitting quietly in space, it is constantly changing. Stars move along enormous orbits around the galactic center. Gas clouds collapse to form new stars. Small galaxies occasionally drift too close and become torn apart by the Milky Way's gravity. Over billions of years, these processes reshape the galaxy's structure. So even as astronomers work to map the Milky Way, the galaxy itself continues evolving. It bends slightly at its edges. Its spiral arms shift and grow. Streams of ancient stars continue orbiting through the halo. Understanding this dynamic system requires observing the sky repeatedly over long periods of time, and that is exactly the kind of observation the next generation of telescopes is designed to perform. Instead of capturing a single image and moving on, these telescopes will watch the sky again and again, building a time-lapse view of the universe. Through that approach, astronomers can detect subtle movements and patterns that reveal the deeper structure of the galaxy, and that brings us closer to understanding why the Vera Rubin Observatory represents such an important step in the search for the Milky Way's true shape. Because after centuries of working around dust, distance, and cosmic fog, astronomers are finally gaining the ability to observe the sky in a way that gathers an extraordinary amount of information. By the time astronomers reached the early years of the 21st century, something had become very clear. The next big step in understanding the Milky Way would not come from simply building a slightly larger telescope. For centuries, most observatories had followed the same basic idea. A telescope would point toward a particular object in the sky. It might observe a distant galaxy, a nebula, a star cluster, or perhaps a planet. The telescope would focus on that target for minutes or hours, gathering as much light as possible in order to reveal faint details. This approach works extremely well for studying specific objects. If astronomers want to understand how stars are born inside a nebula, they can aim a powerful telescope directly at that region and observe it in great detail. If they want to examine the atmosphere of a distant exoplanet, they can concentrate on that star system and collect data for a long period of time. But mapping the Milky Way requires a different strategy. The galaxy contains hundreds of billions of stars spread across enormous distances. Observing a small patch of sky at a time does not easily reveal the large-scale structure of the entire galaxy. To understand that structure, astronomers need to observe vast areas of the sky repeatedly, gathering data about huge numbers of stars. They need to watch how those stars move. They need to see how their brightness changes. And they need to detect patterns that only appear when millions of observations are combined. In other words, they need a telescope designed not just for depth, but for scale. Instead of studying a small part of the sky in extreme detail, this telescope must survey the sky broadly and continuously. That idea eventually led to the design of a new type of observatory, a telescope built specifically to scan enormous portions of the heavens night after night. This observatory would later be named after Vera Rubin, an astronomer whose work helped to reveal one of the most important discoveries in modern astrophysics. Before we talk about the telescope itself, it is worth taking a moment to remember who Vera Rubin was. During the 1960s and 1970s, Rubin studied how stars move within galaxies. By measuring the rotation of spiral galaxies, she discovered something very strange. Stars far from the centre of a galaxy were moving much faster than expected. According to the laws of gravity, stars at the outer edges of a galaxy should orbit more slowly than stars closer to the centre. This is similar to how planets in our solar system behave. Mercury moves quickly around the Sun, while Neptune travels much more slowly. But Rubin's observations showed that galaxies did not behave this way. Stars at the outer edges were moving almost as fast as stars closer to the centre. The only way to explain this motion was to assume that galaxies contain far more mass than we can see. Most of that mass does not emit light. Today we call this invisible material dark matter. Rubin's work helped establish the idea that dark matter plays a major role in shaping galaxies, including the Milky Way itself. Naming the new observatory after her honours that legacy. The telescope built at this site in northern Chile is unlike most telescopes that came before it. It was designed with a single goal in mind: to observe the entire visible sky over and over again. The observatory sits high on a mountain called Cerro Pachón in the Chilean Andes. This location was chosen carefully. The air is dry, the skies are dark, and the atmosphere above the mountain is relatively stable. These conditions are ideal for astronomical observations, but the real innovation lies in the design of the telescope and its camera. Most large telescopes have relatively narrow fields of view. They can see very faint objects, but only within a small portion of the sky at any given time. The Vera Rubin Observatory takes a different approach. Its telescope has an unusually wide field of view, allowing it to capture enormous sections of the sky in a single image. Imagine holding a camera and trying to photograph the night sky. A typical telescope might capture a view similar to looking through a narrow tube, focusing on a tiny region filled with stars. The Rubin telescope, by comparison, acts more like a wide-angle lens. It can see a much larger portion of the sky all at once. This design allows the observatory to survey the sky far more quickly than traditional telescopes. Every few nights it can photograph nearly the entire visible sky. Then it repeats the process again, and again, and again. Over the course of 10 years, the observatory will build an enormous archive of images showing how the sky changes over time. This project is known as the Legacy Survey of Space and Time. The name reflects the two key elements of the mission. First, it creates a detailed survey of the sky. Second, it tracks how the sky evolves across time. Each time the telescope photographs the same region, it captures small changes that occurred since the previous observation. A star might appear slightly brighter or dimmer. An asteroid might move across the field of view. A distant supernova might suddenly appear where no star was visible before. When millions of these observations are combined, astronomers can detect patterns that were previously invisible. For the Milky Way, this kind of survey is incredibly valuable. Instead of studying a few thousand stars, scientists will be able to analyze data from billions of them. That massive data set allows astronomers to trace the structure of the galaxy with far greater precision. Spiral arms can be mapped more clearly. Stellar streams left behind by ancient galactic collisions can be identified more easily. The distribution of stars across the galactic disk can be studied in detail. All of this information helps reveal the true shape of the Milky Way. But gathering this much data requires more than just a wide-angle telescope. It also requires an extraordinary camera. The camera built for the Vera Rubin Observatory is one of the largest digital cameras ever constructed for scientific use. Its detector contains over 3 billion pixels. Each image it captures is so detailed that if you displayed it at full resolution, you could cover a wall with dozens of high-definition television screens and still not show the entire image. Every photograph of the sky taken by this camera records huge numbers of stars and galaxies, and the telescope does not simply take one photograph per night. It captures image after image, scanning the sky methodically. Within a single evening, the observatory can collect tens of terabytes of data. Over the course of the 10-year survey, the total dataset will grow to many petabytes. To put that into perspective, a petabyte equals 1 million gigabytes. Handling this enormous volume of data requires powerful computer systems capable of processing and analyzing images almost immediately after they are captured. Automated software examines each image, identifying objects and measuring their brightness and positions. When something unusual appears, such as a star suddenly brightening or a new object entering the field of view, the system can alert astronomers within minutes. For mapping the Milky Way, this constant stream of observations is extremely valuable, because the structure of the galaxy becomes clearer when we watch how its stars move. Every star travels through space along an orbit determined by the gravitational forces around it. By measuring those motions, astronomers can infer the distribution of mass within the galaxy. They can also identify groups of stars that share similar motions, suggesting that they formed together long ago or belong to the remnants of ancient galaxies absorbed by the Milky Way. Over time, these patterns reveal the hidden architecture of the galaxy. The spiral arms, the stellar halo, the central bar of stars near the galactic center. Even the influence of dark matter can be studied through the motions of stars. This is why a telescope like the Vera Rubin Observatory is so important. It does not simply provide sharper images, it provides a continuous record of the sky, a time-lapse view of the universe, and within that evolving record, the Milky Way slowly reveals its structure. Stars that appear scattered, at first may begin to trace long arcs through space. Clusters of stars may drift together in ways that reveal their shared origins. Gradually, the map of the galaxy becomes more complete. If the Vera Rubin Observatory were simply a large telescope sitting on a mountain, it would still be an impressive instrument. Astronomers have been building large telescopes for centuries, steadily increasing the size of mirrors and improving the precision of their optics. But what truly sets this observatory apart is the device that sits at the end of the telescope, quietly waiting to record the light collected from the sky. Its camera. In everyday life, the word camera usually brings to mind something small and familiar. Perhaps the camera in a smartphone or a digital camera used for taking photographs during a trip. These devices are compact and convenient, capable of capturing detailed images with millions of pixels. The camera at the Vera Rubin Observatory operates on the same general principle, but on a scale that is difficult to imagine. It is the largest digital camera ever built for astronomy. The entire instrument is about the size of a small car. When fully assembled, it weighs several tons. Inside it are dozens of highly sensitive detectors designed to capture faint light from distant stars and galaxies. Together, those detectors form an imaging system containing more than 3 billion pixels. To understand what that means, it helps to think about the images we see every day. A typical high-definition television screen might display around 2 million pixels. A high-resolution photograph from a modern smartphone might contain 10 or 20 million pixels. The Rubin Observatory's camera records images that contain over 3,000 million pixels. If you tried to display one of its photographs at full resolution on ordinary screens, you would need a wall covered with dozens of large monitors placed side by side just to show the entire image clearly. Every time the telescope takes a picture of the sky, it captures an enormous amount of detail. Stars that appear as faint points in smaller telescopes can be measured precisely. Tiny changes in brightness become detectable. Subtle motions of objects across the sky can be tracked over time. But the camera's size is not the only thing that makes it remarkable. It was also designed to see a very wide portion of the sky in a single exposure. Most large telescopes focus on very small regions of the sky. They act like powerful zoom lenses, concentrating on distant objects that appear extremely faint. The Rubin Observatory uses a different approach. Its optical system allows the camera to view a much larger area of the sky at once. In fact, each image covers an area about 40 times the size of the full moon. If you imagine the moon hanging in the night sky, picture 40 copies of that moon placed side by side. That combined area represents roughly the field of view captured by the Rubin camera in a single photograph. This wide field of view allows the telescope to survey the sky quickly and efficiently. Instead of spending an entire night studying a single small patch of stars, the observatory can capture thousands of different regions over the course of a few hours. As the telescope moves from one position to another, the camera continues taking images, building a vast photographic record of the sky. But capturing light from distant stars requires more than just a large detector. Astronomical cameras must also be extremely sensitive. The light arriving from many stars has travelled across enormous distances. Some of those photons began their journey thousands or even tens of thousands of years ago. By the time they reach Earth, only a tiny fraction of that light remains. To detect such faint signals, the Rubin camera uses specialized sensors called charge-coupled devices, often abbreviated as CCDs. These detectors are capable of recording individual photons of light. Each photon striking the detector creates a small electrical signal, which is then measured and stored as part of the image. By collecting many photons over a short period of time, the camera builds a detailed picture of the sky. The Rubin camera contains hundreds of these detectors arranged together in a carefully designed mosaic. Each detector contributes a small piece of the overall image, and when combined they form the full 3 billion pixel photograph. The detectors must also be kept extremely cold during observations. Heat can create unwanted electrical signals that interfere with the detection of faint light. To prevent this, the camera operates at temperatures far below freezing, allowing the sensors to function with maximum sensitivity. Another important feature of the camera is its system of optical filters. Astronomers often observe the sky through different filters that allow only certain wavelengths of light to reach the detector. By comparing images taken through different filters, scientists can learn more about the physical properties of stars and galaxies. For example, some filters emphasize blue light, while others highlight red or infrared wavelengths. Observing an object through multiple filters can reveal information about its temperature, composition, and age. The Rubin camera is equipped with a large rotating filter system that allows the telescope to switch quickly between these different wavelengths. As the observatory surveys the sky, it collects images across several filters, creating a more complete picture of each region. Over time, this approach generates an enormous database of astronomical observations. Every image captured by the Rubin camera is processed by powerful computer systems almost immediately after it is taken. The software identifies objects within the image, measures their brightness and position, and compares the results with previous observations. If something changes, the system notices. Perhaps a star becomes slightly brighter. Perhaps a faint asteroid moves across the field of view. Perhaps a distant supernova suddenly appears where no star was visible before. These changes are detected automatically, allowing astronomers to respond quickly when something interesting happens in the sky. But for understanding the Milky Way, one of the most important capabilities of the Rubin camera is its ability to observe the same stars again and again over many years. Each time the telescope revisits a region of the sky, the camera records another image. At first glance, these images might look nearly identical. But when scientists compare them carefully, small differences begin to appear. A star may have shifted slightly in position compared to earlier observations. Another star may show subtle changes in brightness. A faint object may gradually move across the background of more distant stars. These changes reveal important information. The motion of stars across the sky, known as proper motion, tells astronomers how those stars are moving through the galaxy. By measuring these motions precisely, scientists can trace the orbits of stars around the Milky Way center. When the motions of millions of stars are analyzed together, patterns emerge. Some stars travel in similar directions, suggesting they belong to the same stellar stream. Others follow paths that outline the spiral structure of the galaxy. Gradually, the camera's observations help reveal the architecture of the Milky Way. Another advantage of repeated imaging is the ability to detect very faint objects by combining many observations. A single photograph may not capture enough light to reveal a distant star or galaxy clearly, but if hundreds of images are taken over time, those faint signals can be combined to produce a clearer picture. This technique allows astronomers to study objects that would otherwise remain invisible. The Rubin Observatory will collect millions of such images over its 10-year survey. By the end of the project, the camera will have recorded an extraordinary record of the night sky. Astronomers will be able to explore this dataset for decades, searching for patterns and discoveries that may not even be imagined yet. And somewhere within that enormous archive lies a more detailed understanding of our galaxy. The structure of the Milky Way is written in the positions and motions of its stars. Each observation captured by the Rubin camera adds another small piece to that cosmic map. The more pieces we collect, the clearer the map becomes. Over time, the spiral arms may appear with greater precision. Stellar streams may reveal ancient collisions between galaxies. The distribution of stars in the outer disk may show how the Milky Way has grown over billions of years. All of these discoveries depend on one essential process: watching the sky carefully, night after night. And that is exactly what the Rubin Observatory will do. Its telescope will continue sweeping across the heavens, while its enormous camera records the changing patterns of stars. Those patterns may seem subtle at first, but as the observations accumulate, they begin to form something much larger, a dynamic map of the galaxy itself. And the story of how that map slowly comes into focus begins with a simple idea. What happens when we stop taking isolated snapshots of the universe and instead watch the sky as it changes over time? When most people imagine astronomy, they picture a telescope pointed quietly at the sky, capturing a single beautiful image of distant stars or galaxies. That idea is not entirely wrong. For a long time, many important discoveries came from exactly that approach. Astronomers would carefully observe one region of the sky, gather light for minutes or hours, and produce a detailed photograph of something incredibly far away. Those images often revealed remarkable objects: nebulae glowing with newly forming stars, distant galaxies swirling with billions of suns, exploding supernovae shining briefly before fading into darkness. But those images were still just moments frozen in time, a single snapshot, and the universe is not static. Stars move, galaxies rotate, asteroids drift silently across the darkness. Even the brightness of stars can change, sometimes gradually, sometimes suddenly. When astronomers began thinking about how to understand the Milky Way in greater detail, they realized something important. If you want to understand the structure of a galaxy from the inside, you cannot rely only on snapshots. You must watch how things change. This idea is at the heart of the Vera Rubin Observatory's mission. Instead of taking a photograph of the sky and moving on to a different target, the telescope will return to the same regions again and again. Every few nights, it will scan huge portions of the sky, capturing new images that can be compared with previous ones. At first, the sky may look almost identical from one night to the next. The same stars appear in roughly the same places. The same patterns of constellations remain visible. But when astronomers compare those images carefully, they begin to notice subtle differences. A star might appear slightly brighter or slightly dimmer. A faint point of light might have shifted a tiny distance across the background of distant stars. An object that was not present before might suddenly appear. These changes are usually very small, but small changes, observed repeatedly over time, can reveal enormous amounts of information. Think of it like watching a forest from a distance. If you glance at the forest for a single moment, everything looks still. The trees stand quietly, and the landscape appears unchanged. But if you observe the forest day after day, you begin to notice things you might have missed before. Leaves move in the wind. Animals travel through the undergrowth. New plants grow while older ones decay. Over a longer period, perhaps months or years, the changes become even more noticeable. Trees grow taller, some fall. Entire sections of the forest may transform gradually. In a similar way, the sky reveals its patterns when it is observed continuously. Stars do not appear to move much during a single night. They rise and set due to Earth's rotation, but their positions relative to one another seem fixed. However, over longer timescales, their motion becomes detectable. Each star in the Milky Way travels along its own path through space. These paths are determined by the gravitational forces within the galaxy. The Sun, along with the planets of our solar system, is also moving through the Milky Way at tremendous speed. Even though that speed is more than 200 kilometers per second, the distances involved are so vast that the motion appears extremely slow when observed from Earth. But with precise measurements taken over many years, those tiny shifts can be detected. By observing the sky night after night, the Rubin Observatory will record these small changes with incredible accuracy. The observatory's 10-year survey will produce a time-lapse record of the universe. Every time the telescope revisits a region of the sky, it adds another frame to that cosmic time-lapse. When these frames are combined, astronomers can watch how objects move and change across time. For the Milky Way, this continuous monitoring provides a powerful new tool. Imagine observing a crowded city square from above. If you took a single photograph, you might see hundreds of people scattered across the square. From that image alone, it would be difficult to understand where people came from or where they were going. But if you recorded a video of the same square for several hours, the situation would become much clearer. You would see people entering and leaving. You would notice groups moving together. You might recognize patterns in how individuals cross the square or gather near certain locations. Over time, the behavior of the entire crowd would become easier to understand. The Rubin Observatory will do something similar for the Milky Way. Instead of observing a few thousand stars, it will monitor billions of them. Each star becomes like a person moving through that crowded square. Its motion, brightness, and position provide clues about the larger structure of the galaxy. Some stars will move in ways that reveal the presence of spiral arms. Others will travel together in streams left behind by ancient galaxies that were pulled apart by the Milky Way's gravity. Some stars will display periodic changes in brightness, allowing astronomers to measure their distances more accurately. All of these observations help build a clearer map of our galaxy. But the Rubin Observatory's time-lapse view of the sky will reveal more than just stellar motion. It will also capture many kinds of cosmic events that occur across the universe. Asteroids within our solar system will drift across the camera's field of view, allowing scientists to track their orbits with great precision. Exploding stars known as supernovae will briefly appear as brilliant points of light in distant galaxies. Variable stars will brighten and dim over days or weeks, revealing details about their internal structure. Even rare phenomena such as gravitational lensing events where the gravity of one object bends the light of another, may be detected through subtle changes in brightness. Each night of observation adds more data to the growing archive, and that archive will become one of the most detailed records of the sky ever created. For understanding the Milky Way, this continuous dataset is especially valuable, because the structure of the galaxy is not only written in the positions of its stars, but also in their motions. Stars orbit the galactic center along paths shaped by gravity. Some follow nearly circular orbits within the disk. Others move in elongated paths that carry them far above and below the plane of the galaxy. These different motions reveal information about the distribution of mass within the Milky Way. They can even hint at the presence of dark matter, the invisible material that Vera Rubin helped bring to light through her research. By analysing how stars move across the sky, astronomers can reconstruct the gravitational forces acting within the galaxy, and from those forces they can infer the galaxy's structure. The Rubin Observatory's repeated observations will make it possible to measure these stellar motions for enormous numbers of stars. Patterns that were previously hidden within small datasets may become visible when billions of stars are analysed together. Slowly, the large-scale architecture of the Milky Way begins to emerge. Spiral arms appear as regions where stars share similar motions. Stellar streams form long arcs across the galaxy, marking the remnants of ancient collisions. Clusters of stars move together as they orbit the galactic center. Each pattern tells part of the story of how the Milky Way formed and evolved over billions of years. Watching the sky change night after night also helps astronomers identify objects that might otherwise remain unnoticed. A faint star that brightens suddenly could indicate a distant explosion. A dim object that moves slowly against the background stars might be an asteroid or comet passing through our solar system. These discoveries often begin as small differences between images taken on different nights. Computers compare each new photograph with earlier ones, searching for anything that has changed. When something unusual appears, astronomers can investigate further. But for the purpose of understanding our galaxy, the most valuable discoveries may come from the gradual accumulation of data. As the years pass, the Rubin Observatory will continue collecting observations. Each night adds more information. Each observation sharpens the map. Eventually, the movements of millions upon millions of stars will reveal structures that were previously invisible, and somewhere within those patterns, the true shape of the Milky Way begins to emerge. As more observations accumulate, something interesting begins to happen. At first, the sky simply looks crowded. Stars appear scattered in every direction, each one shining quietly in its own place. To the naked eye, and even to many telescopes, the Milky Way can look like a random collection of lights. But when astronomers begin analysing enormous datasets containing millions or even billions of stars, the randomness slowly starts to disappear. Patterns begin to emerge. These patterns are not obvious in a single photograph. They do not suddenly appear like lines drawn across the sky. Instead, they reveal themselves gradually, through careful measurements of distance, motion, and brightness. When enough stars are studied together, their positions begin to outline larger structures within the galaxy. This is where modern astronomy becomes a bit like studying a massive crowd from above. Imagine standing on a tall building overlooking a busy city square. If you glance down quickly, the people below might appear scattered and unorganized. Individuals walk in different directions, some stopping, others continuing onward. But if you watch carefully for a while, you begin to notice something else. Certain groups of people move along the same paths. Many follow the sidewalks along the edges of the square. Others gather near entrances, benches, or fountains. Although each person moves independently, the larger patterns of motion begin to reveal the design of the square itself. Paths, gathering places, and entrances become clear. The Milky Way works in a very similar way. Each star travels through space along its own orbit around the center of the galaxy. These orbits are shaped by the gravitational forces created by the galaxy's mass. When astronomers track the motions of millions of stars, they begin to see how those orbits cluster into larger patterns. Some stars move together through space as members of stellar streams. These streams are often the remains of smaller galaxies that were pulled apart by the Milky Way's gravity long ago. As those smaller galaxies were gradually torn apart, their stars stretched into long, thin arcs that now orbit the galaxy. Even though those stars are now widely separated, their shared motion reveals their common origin. Other groups of stars form clusters that travel together because they were born in the same region of the galaxy. Stars often form inside giant clouds of gas. When those clouds collapse under gravity, they create groups of stars that initially move through space together. Over millions of years, these clusters gradually disperse as gravitational interactions pull the stars apart. Yet for long periods of time, their shared motion can still be detected. By studying these stellar groups, astronomers can learn about the history of star formation within the Milky Way. But perhaps the most important patterns appear when scientists examine the positions and motions of stars across enormous regions of the galaxy. When millions of stars are mapped together, the structure of the spiral arms begins to appear more clearly. Spiral arms are not solid structures like the arms of a spinning wheel. Instead, they are regions where stars and gas become more densely concentrated. You can think of them as cosmic traffic patterns. As stars orbit the galactic center, they sometimes pass through regions where the gravitational forces cause gas clouds to compress. These compressed clouds can collapse to form new stars. Because new stars are often bright and short-lived, they make spiral arms stand out when astronomers observe distant galaxies. In our own galaxy, identifying these spiral arms is more difficult because we are located inside the disk. But by mapping the positions of young stars, star-forming regions, and clouds of gas, astronomers can trace the locations of these arms. When enough data is collected, the arms begin to appear as sweeping arcs stretching across the galaxy. The Rubin Observatory will play an important role in this process. Its enormous survey of the sky will measure the positions and motions of vast numbers of stars within the Milky Way. By analysing this data, astronomers can identify groups of stars that follow similar orbits. Those groups may outline the spiral structure of the galaxy more clearly than ever before. In addition to spiral arms, another structure begins to appear when large numbers of stars are studied: the central bar of the Milky Way. Many spiral galaxies contain a bar-shaped concentration of stars near their centres. This bar rotates slowly and can influence the motion of stars throughout the galaxy. Observations of infrared light have already revealed that the Milky Way contains such a bar near its centre. However, understanding the exact shape and size of this structure requires detailed measurements of stellar motions. As the Rubin Observatory collects data over many years, astronomers will be able to track how stars move in the inner regions of the galaxy. Those motions will provide clues about the gravitational forces created by the bar. Over time, the structure of the central region may become clearer. But the patterns traced by stars do not stop there. Beyond the main disk of the galaxy lies another structure known as the stellar halo. The halo is a vast spherical region surrounding the Milky Way, containing older stars that orbit far above and below the galactic plane. Many of these stars are extremely ancient, formed during the earlier stages of the galaxy's history. Others may have originated in smaller galaxies that were captured and absorbed by the Milky Way billions of years ago. When astronomers map the motions of halo stars, they often find long streams of stars tracing arcs through space. These stellar streams are the remnants of those ancient mergers. Each stream tells part of the story of how the Milky Way grew over time. The Rubin Observatory's ability to observe faint stars across large areas of the sky will help scientists discover many more of these streams. With enough data, astronomers may be able to reconstruct the sequence of collisions and mergers that built our galaxy. But perhaps one of the most fascinating aspects of these patterns is how they reveal the invisible components of the Milky Way. Earlier, we mentioned dark matter. Dark matter does not emit light, which means it cannot be seen directly with telescopes. yet its gravitational influence affects the motion of stars throughout the galaxy. By measuring how stars move, astronomers can infer the distribution of dark matter. If stars in certain regions move faster than expected, it suggests that additional unseen mass must be present. Over large distances, these measurements reveal that the Milky Way is surrounded by an enormous halo of dark matter, extending far beyond the visible stars. The Rubin Observatory's observations may help refine our understanding of this dark matter halo. By tracking the motions of stars in the outer regions of the galaxy, astronomers can study how gravity behaves at great distances from the galactic center. These measurements may even provide clues about the fundamental nature of dark matter itself. But returning to the patterns formed by stars, there is something quietly remarkable about how they emerge. Each individual star follows its own path through the galaxy. From our perspective on Earth, these paths are almost impossible to notice over short periods of time. Yet when astronomers combine data from millions of stars across many years, those tiny motions reveal something much larger. They reveal the architecture of the Milky Way. Gradually, the scattered lights of the night sky begin to form recognizable structures. Spiral arms curve outward from the central regions. Stellar streams arc through the halo. Clusters of stars move together like drifting islands in space. And as more data continues to arrive, these patterns become clearer. The map of our galaxy grows more detailed with every observation. But one question remains particularly intriguing. What shape do all of these patterns ultimately form? As astronomers gathered more measurements of stars, gas clouds, and stellar motions, something began to take shape within the data. At first, the results were subtle. Individual surveys revealed small pieces of information, and those pieces did not always fit together perfectly. One study might suggest that a certain region of the galaxy contained a spiral arm, while another might indicate a different arrangement of stars nearby. But as the amount of data increased, those small pieces gradually began to connect. The Milky Way was no longer just a vague disk of stars surrounding the solar system. A clearer structure was emerging. Astronomers began to see evidence that our galaxy belongs to a category known as barred spiral galaxies. To understand what that means, it helps to imagine looking at a spiral galaxy from far away. Many spiral galaxies display beautiful arms of stars and gas winding outward from a bright central region. These arms can curve gracefully through space, forming patterns that resemble enormous cosmic pinwheels. But in barred spiral galaxies, the structure near the center looks slightly different. Instead of a simple circular bulge of stars, there is a long bar-shaped concentration of stars stretching across the middle of the galaxy. From the ends of this bar, the spiral arms extend outward into the galactic disk. This arrangement changes how stars move within the galaxy. The bar acts almost like a gravitational engine, influencing the motion of stars and gas clouds across vast distances. Gas can flow along the bar toward the central regions, sometimes fueling intense star formation near the galactic core. Observations in infrared light first revealed that the Milky Way contains such a bar. Because the central regions of our galaxy are hidden behind thick clouds of dust, optical telescopes cannot easily see the dense concentration of stars near the center. Infrared wavelengths, however, can pass through much of that dust. When astronomers used infrared observations to study the galactic center, they discovered that the distribution of stars there is elongated rather than perfectly round. This elongated structure forms the central bar of the Milky Way. It stretches for tens of thousands of light years across the galaxy's inner regions. From the ends of this bar, the spiral arms appear to extend outward through the disk. Mapping those arms has been one of the most challenging tasks in galactic astronomy. Unlike distant galaxies, where the spiral pattern can be photographed directly, the Milky Way must be reconstructed from within. Astronomers use several clues to identify where the spiral arms lie. One clue comes from regions of star formation. Spiral arms are often filled with gas clouds where new stars are born. These star-forming regions contain hot young stars that shine brightly for relatively short periods of time. Because these stars do not live long before exploding as supernovae, they remain close to the places where they formed. By mapping the locations of these young stars and nebulae, astronomers can trace the outlines of spiral arms. Another clue comes from the distribution of gas within the galaxy. Large clouds of hydrogen gas emit radio waves that can be detected with radio telescopes. These gas clouds often align along spiral patterns within the galactic disk. When astronomers map these clouds across the sky, the spiral structure becomes more visible. Combining these observations with measurements of stellar distances and motions allows scientists to build increasingly detailed models of the Milky Way. Over time, a general picture has emerged. The Milky Way appears to have several major spiral arms. Two of the most prominent are known as the Perseus arm and the Scutum Centaurus arm. These arms extend outward from the central bar and curve around the galaxy. Between them lie smaller arms and spurs, including the Orion arm, where our solar system resides. The Orion arm is sometimes described as a minor spiral arm or a spur connecting two larger arms. Although it is smaller than the major arms, it still contains a vast number of stars, including our Sun. From our position inside this arm, we see the Milky Way as a bright band across the sky, because we are looking along the dense plane of the galaxy's disk. This disk itself is enormous. Current estimates suggest that the Milky Way's stellar disk extends roughly 100,000 light-years across, though some stars and gas clouds may lie even farther out. At the centre of this disk lies the galactic bulge, a dense concentration of stars surrounding the supermassive black hole known as Sagittarius A star. This black hole contains millions of times the mass of our Sun and sits at the gravitational centre of the galaxy. Surrounding the disk and bulge is the stellar halo, a vast spherical region containing older stars and globular clusters orbiting far above and below the galactic plane. Beyond the halo lies an even larger halo of dark matter. This invisible component extends far beyond the visible boundaries of the Milky Way and contains most of the galaxy's total mass. The presence of dark matter helps explain why stars in the outer regions of the galaxy orbit at speeds that would otherwise be impossible based on the visible matter alone. Together, these structures form the basic outline of the Milky Way. A barred spiral galaxy with multiple arms, a central bulge, a surrounding halo of stars, and a massive halo of dark matter. Yet even with this general picture, many details remain uncertain. The exact number of spiral arms is still debated. Some models suggest that the galaxy contains 4 main arms, while others propose 2 dominant arms with smaller branches extending between them. The thickness of the galactic disk varies across different regions. The outer edges of the galaxy appear to warp slightly, bending above and below the main plane, and the halo contains countless streams of stars left behind by ancient collisions with smaller galaxies. All of these features add complexity to the Milky Way's structure. As more data becomes available, astronomers continue refining their models. This is where the Rubin Observatory's enormous survey becomes particularly valuable. By tracking the positions and motions of vast numbers of stars across the sky, the observatory will help clarify the arrangement of stars within the galactic disk. Patterns that were once hidden within smaller datasets may become visible when billions of stars are analysed together. The spiral arms may appear with greater precision, the central bar may be mapped more accurately, and the outer edges of the galaxy may reveal structures that were previously difficult to detect. One of the most interesting discoveries in recent years is that the Milky Way's disk is not perfectly flat. Instead, it appears to bend and ripple in certain regions. This warp becomes more noticeable in the outer parts of the galaxy. Astronomers believe that gravitational interactions with nearby satellite galaxies, such as the Sagittarius dwarf galaxy, may be responsible for these distortions. As smaller galaxies pass near the Milky Way, their gravitational pull can disturb the disk, creating waves that ripple through the distribution of stars. These ripples may take millions of years to settle. The Rubin Observatory's long-term survey could help scientists observe these structures in greater detail. By measuring the motions of stars in the outer disk, astronomers may be able to trace how these ripples move and evolve over time. All of these observations contribute to a slowly emerging portrait of the Milky Way. It is not a simple, symmetrical spiral galaxy. It is a dynamic system shaped by gravity, collisions, star formation, and the mysterious influence of dark matter. The more carefully astronomers study it, the more complex it appears. Yet within that complexity lies a recognizable structure, a barred spiral galaxy stretching across tens of thousands of light years, spiral arms sweeping through the disk like enormous arcs of stars and gas. A central region packed with ancient stars orbiting a massive black hole, and far beyond the visible disk, a vast halo of stars and dark matter extending into the depths of space. Understanding this structure requires continuing the process of observation and analysis. Each new survey adds more detail to the map. Each measurement of a star's motion reveals another piece of the galaxy's gravitational architecture. And with instruments like the Rubin Observatory watching the sky night after night, the shape of the Milky Way may soon become clearer than it has ever been before. For anyone looking at photographs of distant galaxies, spiral arms appear obvious and beautiful. Astronomers often show images of galaxies like the Whirlpool Galaxy or the Pinwheel Galaxy, where enormous luminous arms curl outward from a bright central region. These arms seem almost artistic in their design, sweeping through space in graceful arcs filled with stars, gas, and glowing nebulae. From far away, the structure is clear. You can see the arms winding outward like the spokes of a cosmic pinwheel. But the Milky Way does not offer us that same convenient view, because we live inside it. Imagine trying to understand the pattern of a spiral staircase while standing somewhere in the middle of the staircase itself. You might see the steps immediately above and below you, but the overall shape of the structure would be difficult to visualize. You could walk up or down, gathering clues about how the steps curve, but seeing the entire spiral at once would be impossible without stepping outside the building. That is exactly the challenge astronomers face when studying the spiral arms of our own galaxy. For many years, scientists suspected that the Milky Way must contain spiral arms similar to those seen in other galaxies. The distribution of stars and gas across the sky hinted at curved structures extending across the galactic disk. But confirming the exact arrangement of those arms proved extremely difficult. Part of the difficulty came from the same obstacle that has complicated many aspects of galactic astronomy: dust. The disk of the Milky Way contains enormous clouds of dust that obscure our view of distant regions. When astronomers look toward the center of the galaxy, thick dust lanes block much of the visible light. Behind those clouds lie dense star fields and complex structures that are difficult to observe directly. Even when scientists use infrared and radio observations to peer through the dust, measuring distances remains challenging. Knowing that a star or gas cloud lies in a particular direction is only part of the puzzle. To place it within the galaxy's structure, astronomers must also determine how far away it is. Over the years, researchers have developed several methods for estimating those distances. One approach involves studying the locations of massive young stars. These stars are bright, short-lived, and often found near the regions where they formed. Because star formation tends to occur in spiral arms, mapping the positions of these young stars can help trace the arms themselves. Astronomers also study regions where hydrogen gas glows in radio wavelengths. These gas clouds often align along spiral patterns, providing additional clues about the structure of the galaxy. Another useful tool comes from a type of astronomical object known as a maser. Masers are natural sources of microwave radiation produced in certain regions of space, often near young stars. These signals can be measured with extremely high precision using radio telescopes. By observing masers across the Milky Way, astronomers can determine their distances and motions with remarkable accuracy. These measurements provide valuable data points for mapping the spiral arms. Despite all of these techniques, the overall structure of the Milky Way's arms remained uncertain for a long time. Different surveys sometimes produced slightly different results. Some studies suggested that the galaxy contained 4 major spiral arms. Others proposed that 2 dominant arms might exist, with smaller arms branching between them. Part of the confusion came from the complexity of the galaxy itself. Spiral arms are not rigid structures. They are better described as density waves moving through the galactic disk. In a density wave, stars and gas pass through regions where gravitational forces compress the material, triggering star formation. As gas clouds enter these regions, they collapse and form new stars. Those young stars illuminate the spiral arms, making them appear bright in distant galaxies. But the stars themselves do not remain permanently within the arms. Over time, they drift away as they continue orbiting the galactic centre. This means the spiral arms are constantly evolving. They are not fixed lines of stars, but dynamic regions where star formation is more likely to occur. Understanding this behaviour requires studying both the positions of stars and their motions through space. And that is where modern surveys are making a difference. When astronomers analyse the positions and velocities of millions of stars, patterns begin to appear that hint at the locations of spiral arms. Clusters of young stars align along certain regions. Gas clouds form long arcs across the disk. Stellar motions reveal gravitational patterns that correspond to spiral structures. Gradually, these observations begin to form a map. The Milky Way appears to contain several major arms extending from the ends of its central bar. 2 of the most prominent arms are the Scutum Centaurus arm and the Perseus arm. These arms curve outward through the disk, containing large numbers of stars, gas clouds, and star-forming regions. Between them lie smaller structures including the Sagittarius arm and the Orion arm. The Orion arm is particularly interesting for a simple reason. That is where we are. Our solar system sits within this smaller arm, roughly halfway between the centre of the galaxy and its outer edge. From our location inside the Orion arm, we look outward toward the Perseus arm and inward toward the Sagittarius arm. This position offers a fascinating view of the Milky Way's disk, but it also complicates efforts to map the spiral structure. Because we are embedded within one of the arms, the stars surrounding us fill the sky in every direction. Distinguishing where one arm ends and another begins requires extremely careful measurements. Modern instruments such as the Gaia spacecraft have already improved our understanding of these structures by measuring the distances and motions of vast numbers of stars. The Rubin Observatory will add another powerful layer of information. Its survey will repeatedly observe enormous regions of the sky, tracking how stars move and how their brightness changes over time. With billions of stars included in its dataset, astronomers will be able to analyse the Milky Way's structure with unprecedented detail. Clusters of stars that share similar motions may reveal hidden spiral patterns. Regions of star formation may trace the outlines of arms more clearly than before. Even faint stars in distant parts of the galaxy may contribute to the emerging map. As this information accumulates, the spiral arms of the Milky Way may finally become easier to trace. When people imagine the Milky Way, the picture that often comes to mind is fairly simple. A wide, flat disk of stars spinning gently in space. In many diagrams, that disk appears perfectly smooth, almost like a giant vinyl record made of hundreds of billions of stars. Spiral arms curve across its surface, and a bright central bulge rises in the middle. This image is useful for understanding the general structure of the galaxy. But the real Milky Way is not quite that tidy. As astronomers began studying the outer regions of the galaxy more carefully, they noticed something unexpected. The disk is not perfectly flat. Instead, it bends. If you could somehow step far outside the Milky Way and look back at it from a distance, you would see that the outer edges of the disk do not remain in a straight plane. In some areas, the stars curve slightly above the central plane of the galaxy. In other areas, they dip below it. This distortion is known as the galactic warp. To picture this, imagine holding a large dinner plate. At first, the plate is perfectly flat. But if you gently bend the edges upward on one side and downward on the other, the plate begins to twist slightly. The center remains mostly flat, but the outer regions curve in different directions. Something similar happens in the Milky Way. Near the central regions of the galaxy, the disk remains relatively flat, but as you move farther from the center, especially beyond the main spiral arms, the disk gradually begins to warp. Stars and gas clouds in these outer regions follow orbits that carry them above or below the central plane. This warp is not dramatic enough to notice when looking at the Milky Way with the naked eye. From our position inside the disk, the galaxy still appears as a relatively straight band of stars stretching across the sky. But when astronomers measure the positions and motions of stars across great distances, the bending becomes clear. The first strong evidence for the warp came from observations of hydrogen gas. As we discussed earlier, hydrogen emits radio waves at a wavelength of 21 centimeters. Radio telescopes can detect this signal even in regions of the galaxy that are hidden by dust. When astronomers mapped hydrogen gas across the Milky Way using radio observations, they discovered that the gas did not lie in a perfectly flat disk. Instead, the outer parts of the disk seem to curve upward in one direction and downward in the opposite direction. At first, scientists wondered whether this effect might be caused by errors in the measurements. But as more observations were collected, the pattern became consistent. The Milky Way's disk really does bend. Later studies confirmed that stars in the outer disk follow similar warped paths. The entire structure of the galaxy appears to ripple slightly as it extends outward. This discovery raised an important question. What causes the warp? Several explanations have been proposed, and the answer may involve a combination of different factors. One possible cause is the gravitational influence of nearby galaxies. The Milky Way does not exist alone in space. It is surrounded by dozens of smaller satellite galaxies that orbit around it. Two of the most prominent are known as the Large Magellanic Cloud and the Small Magellanic Cloud. These galaxies are visible from the southern hemisphere as faint cloudy patches in the night sky. Although they are much smaller than the Milky Way, their gravitational pull can still influence our galaxy. As they orbit the Milky Way, their gravity may tug on the outer regions of the galactic disk, creating distortions that slowly ripple through the stars and gas. Another likely contributor is the Sagittarius dwarf galaxy. This small galaxy has been passing through the Milky Way's outer regions for millions of years. As it moves through the galaxy, the gravitational interaction between the two systems may disturb the disk, producing waves and ripples in the distribution of stars. Astronomers sometimes compare this process to dropping a pebble into a pond. When the pebble hits the water, waves spread outward across the surface. In the case of the Milky Way, the pebble might be a passing dwarf galaxy, and the waves travel through the disk of stars and gas. Over time, these waves can create long-lasting distortions. Another possibility involves the invisible halo of dark matter surrounding the Milky Way. Dark matter makes up most of the galaxy's mass, and it extends far beyond the visible disk of stars. If the dark matter halo is not perfectly symmetrical, its gravitational influence could pull the outer disk slightly out of alignment. This could also contribute to the warp observed in the Milky Way. Understanding exactly how these forces interact is still an active area of research. The warp may be the result of multiple influences acting together over billions of years, and because the galaxy continues to interact with its surroundings, the shape of the disk may continue to change slowly over time. This is where long-term observations become especially valuable. By measuring the positions and motions of stars across the outer disk, astronomers can study how the warp behaves. Does it remain stable over time? Does it shift or ripple as gravitational interactions occur? These questions require precise measurements of enormous numbers of stars. Modern surveys such as the Gaia mission have already provided detailed data about the positions and motions of millions of stars in the Milky Way. The Vera Rubin Observatory will add another powerful data set to this effort. Because the observatory repeatedly observes large portions of the sky, it can track how stars move over many years. These measurements will help astronomers map the three-dimensional structure of the galaxy with greater accuracy. If the warp of the Milky Way changes over time, those changes may become visible in the motion of stars within the disk. Even small shifts in the positions of stars can reveal how gravitational forces are shaping the galaxy. The warp also provides clues about the history of the Milky Way. If the distortion was caused by interactions with other galaxies, studying its shape may help astronomers reconstruct those past encounters. In other words, the bending of the disk may act like a record of ancient events. Every ripple in the galaxy's structure may carry information about collisions, mergers, or gravitational influences that occurred millions or billions of years ago. This idea connects the warp to another fascinating feature of the Milky Way. Beyond the disk, stars are not distributed randomly. Many of them travel in long, thin streams that arc through the galaxy's halo. These stellar streams are remnants of smaller galaxies and star clusters that were gradually torn apart by the Milky Way's gravity. As those systems were disrupted, their stars spread along the paths of their original orbits, forming extended trails across space. Mapping these streams has become one of the most important ways astronomers study the formation of our galaxy, because each stream represents a piece of the Milky Way's past, and when scientists examine these structures carefully, they begin to see how the galaxy grew over billions of years through the slow accumulation of smaller systems. But those stellar streams also interact with the galactic disk. Their gravitational influence, along with that of satellite galaxies, may contribute to the ripples and distortions observed in the disk itself. In this way, the warp of the Milky Way connects to a larger story, the story of how galaxies grow, collide, and evolve across cosmic time. The Milky Way is not a static structure. It is a dynamic system constantly shaped by gravity, star formation, and interactions with its surroundings. Even the disk beneath our solar system is slowly shifting as stars orbit the galactic center and respond to the gravitational forces around them. Understanding these motions requires tracking enormous numbers of stars across vast distances. And that is exactly what modern astronomical surveys are beginning to accomplish. With each new data set, the map of the Milky Way becomes more detailed. The spiral arms appear more clearly. The central bar becomes better defined. The warp of the disk reveals how the galaxy bends and ripples across space. Long before astronomers had detailed maps of the Milky Way, they occasionally noticed something unusual in the sky. Certain stars did not appear to move entirely independently. When scientists carefully measured their positions and motions, small groups of stars sometimes seemed to drift together across space, as though they shared a common journey. At first, these observations were difficult to interpret. Stars are scattered throughout the galaxy, and from our position inside the Milky Way, many of them appear close together simply because they lie along the same line of sight. But as measurements improved, astronomers began to notice that some stars were not only close in the sky, they also moved in the same direction, at nearly the same speed. This suggested that these stars were physically related. They were not just neighbours by chance, they were travelling together. Over time, researchers discovered that many of these stars were arranged along long, thin structures stretching across the galaxy. These structures came to be known as stellar streams. You can imagine a stellar stream as a river of stars flowing quietly through space. Each star follows its own orbit around the galactic centre, but the stars in the stream remain loosely connected by their shared origin. And that origin often lies in the distant past. Most stellar streams are believed to form when smaller galaxies or star clusters pass too close to the Milky Way. Our galaxy's gravity is extremely strong, especially near its centre. When a smaller system drifts into this gravitational field, tidal forces begin to pull it apart. The stars within the smaller galaxy are gradually stripped away. Some drift ahead along the orbit, while others trail behind. Over time, these stars spread out along long arcs that wrap around the Milky Way. The original galaxy may eventually disappear completely, leaving only the stream behind. To an observer mapping the sky, the result appears as a faint ribbon of stars stretching across enormous distances. Some stellar streams extend tens of thousands of light years across the galaxy. One of the most famous examples is the Sagittarius Stream. This stream is the remnant of the Sagittarius dwarf galaxy, a small galaxy that has been orbiting the Milky Way for billions of years. As it passed repeatedly through the Milky Way's disk, gravitational forces slowly tore it apart. Its stars were pulled away and stretched into long trails that now wrap around the galaxy. Today, the Sagittarius Stream forms a huge arc across the sky, containing stars that once belonged to a separate galaxy. Discoveries like this change the way astronomers think about the Milky Way. For a long time, people imagined our galaxy as a relatively stable structure that formed early in cosmic history and remained mostly unchanged. But stellar streams tell a different story. They reveal that the Milky Way has been growing and evolving over billions of years. Smaller galaxies have been captured and absorbed. Star clusters have been disrupted. Each event leaves behind faint traces in the form of stellar streams. These streams act almost like archaeological evidence in the sky. By studying their shapes and motions, astronomers can reconstruct the past interactions that shaped the galaxy. The direction of a stream shows the orbit of the original system. The distribution of stars along the stream reveals how long ago the disruption occurred, and the motion of those stars provides clues about the gravitational forces within the Milky Way. This last point is especially important. Stellar streams are extremely sensitive to gravity. If something disturbs the gravitational field of the galaxy, the shape of a stream may change. The stream might bend slightly, or its stars might shift into unexpected positions. Because of this sensitivity, stellar streams can act as probes of the invisible structures within the galaxy. Earlier we mentioned dark matter, the mysterious substance that appears to make up most of the Milky Way's mass. Dark matter does not emit light, so astronomers cannot see it directly, but it still exerts gravitational influence on stars. When scientists examine the shapes of stellar streams, they can detect subtle disturbances caused by the presence of dark matter. If a stream passes near a clump of dark matter, the gravitational pull may alter the stream's path. These distortions can help astronomers learn about the distribution of dark matter throughout the galaxy. In this way, the quiet rivers of stars drifting through space become powerful tools for understanding the hidden structure of the Milky Way. However, detecting these streams is not easy. Many of them are extremely faint. Their stars may be spread out across huge regions of the sky, making them difficult to distinguish from the countless other stars in the galaxy. For many years, only a few stellar streams were known. But as astronomical surveys became more powerful, more streams began to appear. The Gaia spacecraft, for example, has already revealed dozens of stellar streams by measuring the positions and motions of millions of stars. When astronomers analysed Gaia's data, they noticed that certain groups of stars shared similar motions through space. Tracing those motions revealed long arcs that corresponded to previously unknown stellar streams. These discoveries suggested that the Milky Way's halo contains far more streams than scientists had previously imagined. Some may be the remnants of dwarf galaxies that merged with the Milky Way billions of years ago. Others may have originated from star clusters that were gradually torn apart by tidal forces. Each stream represents a chapter in the galaxy's history, and many of those chapters remain only partially understood. This is where future surveys become extremely valuable. The Vera Rubin Observatory will observe enormous numbers of stars across wide areas of the sky. Its repeated observations will help astronomers measure stellar motions with greater precision. When scientists analyze this data, they may discover many more stellar streams hidden within the Milky Way's halo. Some streams may be extremely faint, consisting of stars that have spread out over vast distances. Others may appear as relatively dense arcs crossing the galaxy. With enough data, astronomers may be able to map these structures in remarkable detail, and when those streams are traced across the sky, they reveal something fascinating. They show how the Milky Way has grown over time. Instead of forming all at once, the galaxy appears to have assembled itself gradually through a process known as hierarchical merging. Small galaxies formed first in the early universe. Over time, gravity pulled them together. Larger galaxies grew by capturing and absorbing these smaller systems. The Milky Way is no exception. Its halo contains the remains of many ancient galaxies that were swallowed long ago. The stars from those galaxies now travel through space as part of stellar streams. Studying these streams helps astronomers reconstruct the Milky Way's formation history. It also provides insight into the larger process of galaxy formation across the universe. When we picture the Milky Way, most of the attention naturally goes to the bright disk. That disk contains the spiral arms, the glowing clouds of gas, and the countless stars that form the familiar band of light across the night sky. It is the region where most of the visible activity of the galaxy takes place. But the Milky Way does not end at the edge of that disk. Far beyond the spiral arms, stretching outward in every direction, lies another enormous structure. This structure is known as the galactic halo. Unlike the disk, the halo is not flat. Instead, it forms a roughly spherical region surrounding the entire galaxy. It extends above and below the galactic plane and reaches far beyond the outermost spiral arms. From our position inside the Milky Way, the halo is difficult to notice. The stars within it are much more widely spaced than those in the disk, and many of them are faint. Because they are spread across such large distances, they do not create the bright band of light that we see when looking along the galactic plane. For a long time, astronomers were not entirely sure how large this halo might be. But as observations improved, it became clear that the halo is enormous. Some estimates suggest that it extends hundreds of thousands of light-years from the galactic centre. In fact, parts of the halo may reach halfway toward the nearest large galaxy, the Andromeda Galaxy. Within this vast region reside some of the oldest stars in the Milky Way. Many halo stars formed more than 10 billion years ago during the early stages of the galaxy's history. These stars are often smaller and less rich in heavy elements than the younger stars found in the disk. Astronomers describe them as metal poor, meaning they contain fewer elements heavier than hydrogen and helium. This chemical composition provides an important clue about their age. In the early universe, heavy elements were much rarer. They were created gradually inside stars and released into space through supernova explosions. Because halo stars formed so early, before many generations of stars had enriched the galaxy with heavier elements, they still carry the chemical signature of that ancient time. Studying these stars helps astronomers understand what the Milky Way looked like when it was young. The halo also contains another fascinating type of object known as globular clusters. Globular clusters are dense spherical groups of stars bound together by gravity. Each cluster can contain hundreds of thousands of stars packed into a relatively small region of space. These clusters orbit the Milky Way far above and below the galactic disk. When astronomers observe globular clusters through powerful telescopes, they appear as brilliant balls of tightly packed stars. Many of them are extremely old. Some globular clusters formed more than 12 billion years ago, not long after the universe itself began. This makes them some of the oldest surviving structures in our galaxy. By studying the ages and compositions of globular clusters, astronomers can learn about the earlier stages of galactic evolution. But the halo contains more than just ancient stars and clusters. As we discussed earlier, it is also filled with stellar streams. These streams represent the remnants of smaller galaxies and star clusters that were gradually pulled apart by the Milky Way's gravity. Over billions of years, the Milky Way has absorbed many such systems. Each time a smaller galaxy ventured too close, tidal forces stretched it apart, scattering its stars along long orbital paths. The result is a halo filled with faint rivers of stars drifting through space. Mapping these streams helps astronomers reconstruct the Milky Way's history of mergers and interactions. Some streams are relatively recent, formed when a dwarf galaxy was disrupted within the last few billion years. Others are far older. Their stars spread so widely that the original structure of the stream has become difficult to recognize. With each new astronomical survey, more of these streams are discovered. The halo, once thought to contain only a sparse population of stars, is now understood to be a complex environment shaped by ancient collisions and gravitational interactions. And yet, even the stars and clusters within the halo represent only a small fraction of its total mass. Most of the halo is made of something invisible, dark matter. Earlier we mentioned that Vera Rubin's work helped reveal the presence of dark matter in galaxies. When astronomers measured how stars orbit within spiral galaxies, they found that the visible matter alone could not explain the observed speeds. Stars in the outer regions were moving far too quickly. If only the visible stars and gas were present, those outer stars should have drifted away from the galaxy. The fact that they remained bound suggested that an enormous amount of unseen mass must be present. This unseen mass forms a massive halo surrounding the galaxy. The dark matter halo of the Milky Way is believed to extend far beyond the visible disk and stellar halo. Although we cannot see dark matter directly, its gravitational influence shapes the motions of stars throughout the galaxy. Stellar streams within the halo, for example, often follow paths determined by the distribution of dark matter. By studying how these streams move and bend, astronomers can infer the structure of the dark matter halo. Some researchers believe that dark matter may form clumps within the halo. If a stellar stream passes near one of these clumps, the stream's path may be slightly distorted. Detecting such distortions could provide valuable clues about the nature of dark matter itself. The Vera Rubin Observatory is expected to contribute significantly to this research. Its survey will detect vast numbers of faint stars in the halo. By measuring their positions and motions over time, astronomers can identify new stellar streams and map the halo's structure with greater detail. These observations may help answer questions about how the halo formed and how dark matter is distributed throughout the galaxy. Another interesting aspect of the halo is its connection to the Milky Way's neighbouring galaxies. The Milky Way is part of a small group of galaxies known as the Local Group. This group includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. Some of these dwarf galaxies orbit the Milky Way within its halo. Over time, gravitational interactions may pull these smaller galaxies apart, adding their stars to the halo. In this way, the halo acts as a kind of record of the Milky Way's past interactions with its neighbours. Every stream of stars, every disrupted cluster, and every ancient star within the halo tells part of that story. From our vantage point inside the disk, it can be difficult to appreciate the full scale of this structure. The halo surrounds us in all directions, extending far beyond the bright band of the Milky Way we see in the sky. If we could travel far above the galactic plane and look back toward the galaxy, we would see the disk glowing with countless stars, while the halo would appear as a faint diffuse cloud surrounding it. And beyond that cloud would lie the vast halo of dark matter, invisible yet containing most of the galaxy's mass. Together these structures define the true size and shape of the Milky Way. A rotating disk of stars, a central bar and bulge, a warped outer disk, a halo of ancient stars and globular clusters, and an enormous dark matter halo extending far into space. Understanding how all of these components fit together is essential for answering one of the biggest questions in astronomy. What holds the galaxy together? When astronomers first tried to understand how galaxies move, they expected the answer to be fairly straightforward. Gravity, after all, is a familiar force. If you know how much mass an object contains, you can calculate how strongly its gravity will pull on other objects nearby. This principle works extremely well when studying the solar system. The Sun contains most of the mass in our planetary system, and its gravity controls the motion of the planets. Mercury, which orbits closest to the Sun, moves quickly along a tight path. Neptune, far out at the edge of the solar system, travels more slowly along a much larger orbit. This pattern follows the basic rules of gravity. So when astronomers began measuring the rotation of galaxies, they expected to see something similar. Stars near the centre of a galaxy should move quickly, where the gravitational pull is strongest. Stars farther out should move more slowly, where the influence of the central mass becomes weaker. But when scientists carefully measured the motions of stars in spiral galaxies, something surprising appeared. The stars in the outer regions were not slowing down. Instead, they were moving almost as quickly as stars much closer to the centre. At first, this result seemed puzzling. If only the visible stars and gas in the galaxy were producing gravity, the outer stars should not be able to maintain such high speeds. According to the equations of gravity, those stars should drift away from the galaxy over time, yet they remained bound in stable orbits. Something else had to be providing additional gravitational pull. This mysterious extra gravity could not be explained by the visible matter alone, and that realization led to one of the most important discoveries in modern astronomy. Galaxies contain enormous amounts of invisible mass. This invisible material is what we now call dark matter. The term dark does not mean that the material is simply dim or hidden behind dust. Instead, it means that the substance does not interact with light at all. Dark matter does not emit light. It does not reflect light. It does not absorb light. As far as our telescopes can tell, it is completely invisible, and yet its gravitational influence is unmistakable. The first strong evidence for dark matter in galaxies came from the work of Vera Rubin and her colleagues in the 1970s. Rubin studied how stars move within spiral galaxies, including our own Milky Way. When she measured the rotation speeds of stars at different distances from the galactic centre, she discovered that the rotation curve of galaxies remained surprisingly flat. In other words, stars far from the centre were orbiting at nearly the same speed as those closer in. This observation suggested that galaxies must contain much more mass than we can see. To explain the motions of stars, astronomers proposed that galaxies are surrounded by enormous halos of dark matter. These halos extend far beyond the visible disks of stars and gas. In fact, most of a galaxy's total mass may reside in this invisible halo. For the Milky Way, the dark matter halo is believed to stretch hundreds of thousands of light-years from the galactic centre. Although the stars we see form a disk roughly 100,000 light-years across, the dark matter halo extends much farther. It surrounds the galaxy like a vast, invisible sphere. Because dark matter interacts only through gravity, it does not collapse into stars or planets the way ordinary matter does. Instead, it forms a diffuse but massive structure that acts as the gravitational framework of the galaxy. Some astronomers describe this framework as the hidden skeleton of the Milky Way. Just as a skeleton supports the structure of a body, the dark matter halo provides the gravitational support that holds the galaxy together. Without it, the outer stars would not remain bound to the galaxy. The spiral arms would not maintain their shape, and the galaxy itself might not have formed in the way we observe today. Understanding the distribution of dark matter within the Milky Way is one of the major goals of modern astronomy. But studying something that cannot be seen presents obvious challenges. Astronomers must rely on indirect methods. Instead of observing dark matter directly, they examine its gravitational effects on visible objects. One way to do this is by studying the motions of stars. Every star in the galaxy moves under the influence of gravity. By measuring how fast stars travel and how their orbits change across the galaxy, scientists can infer how much mass must be present to produce those motions. If stars in a certain region move faster than expected, it suggests that additional unseen mass is present there. Large surveys of stellar motions allow astronomers to map the gravitational field of the Milky Way. From that map, they can estimate the distribution of dark matter throughout the galaxy. Another useful method involves studying stellar streams. As we discussed earlier, stellar streams are long ribbons of stars left behind when smaller galaxies are torn apart by the Milky Way's gravity. Because these streams are stretched across enormous distances, their shapes are extremely sensitive to gravitational forces. If the distribution of dark matter within the galaxy is uneven, the paths of these streams may bend or distort in subtle ways. By measuring those distortions, astronomers can learn about the structure of the dark matter halo. Some theories suggest that dark matter may form small clumps scattered throughout the halo. If one of these clumps passes near a stellar stream, it could leave a detectable signature in the stream's shape. Finding such signatures could help scientists understand the nature of dark matter itself. The Vera Rubin Observatory is expected to play an important role in this research. Because the observatory will detect vast numbers of stars across the Milky Way, it will provide extremely detailed measurements of stellar positions and motions. With this data, astronomers can study the gravitational forces acting throughout the galaxy with unprecedented precision. The motions of stars in the outer halo in particular may reveal how dark matter is distributed far from the galactic centre. These observations could help answer some of the most fundamental questions in astrophysics. What is dark matter made of? Why does it interact with gravity but not with light? How did it influence the formation of galaxies in the early universe? Although dark matter remains mysterious, its presence is essential for understanding the structure of the Milky Way. Without it, the galaxy would look very different. The spiral arms might not exist in their current form. The stellar halo might not extend as far as it does. Even the process of galaxy formation might have followed a completely different path. For now, dark matter remains invisible to our telescopes, but its influence can be traced through the motions of stars, the shapes of stellar streams, and the overall structure of galaxies. As astronomers continue mapping the Milky Way with new instruments and surveys, the hidden skeleton of the galaxy becomes easier to study. Each measurement of a star's motion adds another clue. Each discovery of a new stellar stream reveals another piece of the gravitational puzzle, and slowly, the invisible structure holding the galaxy together begins to take shape. Yet while dark matter forms the framework of the Milky Way, our own place within that enormous structure remains surprisingly modest. Think for a moment about the idea of an address. In everyday life, an address is something simple and practical. It tells people where a house is located, how to find a building, or where a letter should be delivered. A few lines of text can guide someone across an entire city. But when astronomers talk about our address in the universe, the idea becomes much larger. Instead of a street or a neighbourhood, the address stretches across enormous distances. It describes where our planet sits within a vast cosmic structure that extends tens of thousands of light years in every direction. And interestingly, our location within the Milky Way turns out to be neither especially central nor especially remote. It is somewhere in between. To understand this cosmic address, we can begin with the most familiar point in the chain: Earth. Our planet orbits the Sun once every year, travelling along a path roughly 150 million kilometres from our star. This orbit forms the basic scale of the solar system, a region dominated by the Sun's gravity. The solar system itself contains a collection of planets, moons, asteroids, comets, and distant icy objects far beyond the orbit of Neptune. Yet even this entire system is extremely small compared to the galaxy around it. If the Milky Way were reduced to the size of a large continent, the solar system would be smaller than a grain of sand. The next step in the address is the Sun. Our star is one among hundreds of billions of stars in the Milky Way. It formed about 4.6 billion years ago from a cloud of gas and dust within the galaxy's disk. Like nearly all stars in the Milky Way, the Sun does not remain stationary. It travels through space, orbiting the centre of the galaxy along a vast circular path. This orbit is enormous. The distance between the Sun and the galactic centre is roughly 26,000 light-years. A light-year is the distance light travels in 1 year, which is about 9.46 trillion kilometres. So when we say 26,000 light years, we are describing a distance that is almost impossible to visualise directly. Yet that distance places the solar system comfortably within the Milky Way's disk, neither near the central bulge nor near the far outer edge. The Sun sits in a region known as the Orion Arm, sometimes called the Orion Spur. This is not one of the galaxy's largest spiral arms. Instead, it is a smaller structure located between two major arms. On one side lies the Sagittarius Arm, close to the galactic centre. On the other side lies the Perseus Arm, farther out in the disk. Our solar system occupies a quiet section of this intermediate region. From here, the stars of the Milky Way surround us in all directions. When you look up at the night sky and see the Milky Way stretching across the darkness, you're actually looking along the plane of the galaxy's disk. In that direction, your line of sight passes through enormous numbers of stars packed within the spiral arms. That is why the Milky Way appears as a dense band of light. In contrast, when you look away from that band toward the regions above or below the galactic plane, the number of visible stars becomes smaller. This simple observation reveals something about our position. We are inside the disk, and because we are inside it, we see the galaxy from the side rather than from above. Understanding our location within this disk required decades of careful measurement. Earlier in the 20th century, astronomers debated whether the Sun might lie near the centre of the Milky Way. Some early maps even suggested that our solar system was close to the middle of the galaxy. But as more observations were collected, that idea gradually changed. By studying globular clusters and measuring distances to stars, astronomers realised that the centre of the Milky Way lies far away in the direction of the constellation Sagittarius. Today we know that a supermassive black hole, known as Sagittarius A star, occupies that central region. The stars surrounding this black hole move along extremely fast orbits, revealing the immense gravitational pull concentrated there. Compared to that crowded central environment, the region where our solar system resides is relatively calm. The Orion Arm contains many stars, but they are spaced far enough apart that encounters between star systems are extremely rare. This relative isolation may have played an important role in the history of life on Earth. If the Sun had formed much closer to the galactic centre, the environment might have been far more hazardous. The central regions of the galaxy contain dense clusters of stars, intense radiation, and frequent supernova explosions. These conditions could disrupt planetary systems or expose planets to dangerous levels of radiation. In contrast, the Orion Arm provides a more stable environment. Stars here are separated by several light years on average. The solar system can orbit the galaxy without experiencing frequent close encounters with other stars. Some scientists refer to this region as part of the galactic habitable zone. This concept suggests that certain parts of a galaxy may be more favourable for the development of life than others. Too close to the galactic centre, and the environment may be too violent. Too far out in the outer disk, and the supply of heavy elements needed to form planets might be limited. Our location appears to fall within a comfortable middle region. That does not mean the galaxy is completely quiet around us. The solar system still travels through regions of interstellar gas and dust as it orbits the galactic centre. Over tens of millions of years, these encounters can slightly influence the distant objects in the outer solar system. But overall, our position within the Orion Arm seems to offer a relatively stable place within the galaxy. Of course, even this quiet region is part of a much larger journey. The Sun moves around the Milky Way at a speed of roughly 220 kilometers per second. At that speed, the solar system completes one full orbit around the galactic centre, roughly every 225 to 250 million years. Astronomers sometimes refer to this as a galactic year. During the time since dinosaurs first appeared on Earth, our solar system has completed only a single orbit around the galaxy. Over the entire history of Earth, the Sun has circled the Milky Way fewer than 20 times. This slow but steady motion means that the solar system's galactic environment changes gradually over extremely long periods. Stars drift closer and farther away. The the solar system passes through different regions of the spiral arms. Occasionally, nearby supernova explosions may occur within a few hundred light years. These events can influence the cosmic radiation environment surrounding Earth. Yet most of the time, the journey remains uneventful. The Sun quietly follows its path through the galaxy, carrying the planets along with it. When astronomers attempt to visualize this motion, they often imagine the solar system tracing a long circular path around the Milky Way center. But the motion is actually more complicated than a simple circle. As the Sun orbits the galaxy, it also moves slightly up and down relative to the galactic plane. This vertical motion causes the solar system to oscillate gently above and below the disk over tens of millions of years. The path resembles a slow wave as the Sun travels through space. These oscillations may play a role in how the solar system interacts with interstellar clouds and cosmic radiation over long timescales. They also illustrate an important point. Our address in the galaxy is not fixed. It changes gradually as the solar system continues its orbit. Over millions of years, the stars visible in our night sky slowly shift positions. Constellations that appear familiar today will look very different in the distant future. Stars move along their own paths through the galaxy, and their relative positions change as time passes. The Rubin Observatory's long-term survey will help astronomers measure these motions with extraordinary precision. By tracking how stars shift across the sky over many years, scientists can determine their velocities and trajectories. This information helps reveal the structure of the Milky Way's disk and spiral arms. It also helps refine our understanding of where the solar system sits within the larger galactic environment. Because when billions of stars are measured together, their motions begin to reveal the overall pattern of the galaxy. The Orion arm, the neighbouring spiral arms, and the central bar all become easier to map. And within that map, our solar system occupies a very small but clearly defined position. A quiet location within a minor spiral arm, orbiting the centre of a galaxy filled with hundreds of billions of stars. Across timescales far longer than a human lifetime, the Milky Way continues to evolve. From our everyday perspective, the galaxy seems completely still. The same stars appear night after night, and the constellations look almost identical from year to year. Even over centuries, the sky changes only slightly. Yet this calm appearance hides a much more dynamic reality. Every star in the Milky Way is moving. Gas clouds drift through the disk. New stars form while older stars end their lives in powerful explosions. Small galaxies pass nearby, sometimes becoming stretched and absorbed by the Milky Way's gravity. Although these changes unfold slowly, together they shape the structure of the galaxy across billions of years. The Milky Way we observe today is the result of this long history of transformation. To understand how the galaxy continues to change, astronomers often begin by examining its motion through space. The Milky Way is not isolated. It belongs to a collection of galaxies known as the Local Group. This group contains several large galaxies, including the Andromeda Galaxy and the Triangulum Galaxy, along with dozens of smaller dwarf galaxies. All of these systems move through space under the influence of gravity. Among them, the most important interaction involves the Milky Way and the Andromeda Galaxy. Andromeda lies about 2.5 million light-years away and is slightly larger than our own galaxy. For many years, astronomers measured its motion carefully to determine whether it was drifting away or moving toward us. The result turned out to be remarkable. The Andromeda Galaxy is slowly approaching the Milky Way. It is travelling toward us at a speed of roughly 110 kilometers per second. Although that may sound fast, the enormous distance between the two galaxies means that the encounter will not happen any time soon. Current estimates suggest that the Milky Way and Andromeda will begin interacting in about 4 billion years. At that time, the two galaxies will not simply collide like solid objects. Instead, their stars will pass through one another while gravity reshapes both systems. Over hundreds of millions of years, tidal forces will stretch and distort the galaxies. Spiral arms may become elongated, Streams of stars may be thrown outward into space. Eventually, the two galaxies are expected to merge into a single, much larger galaxy. Astronomers sometimes refer to this future system as Milky Way. Although this event lies far in the future, smaller interactions are already happening within the Milky Way today. The galaxy is surrounded by numerous dwarf galaxies that orbit within its halo. Some of these galaxies have already begun to break apart under the influence of the Milky Way's gravity. The Sagittarius dwarf galaxy is one example. This small galaxy has been passing through the Milky Way's outer regions for billions of years. Each time it travels through the galactic disk, tidal forces strip away some of its stars. These stars form long streams that now wrap around the galaxy. Over time, the remaining core of the Sagittarius dwarf galaxy will likely disappear completely as its stars disperse into the Milky Way's halo. Other dwarf galaxies may experience similar fates. This process of gradual merging plays an important role in how large galaxies grow. In the early universe, galaxies were much smaller. Over time, gravity pulled them together, forming larger systems through repeated mergers. The Milky Way has grown in exactly this way. Many of the stars in its halo once belonged to smaller galaxies that were absorbed long ago. Even today, the process continues. The Milky Way slowly gathers new material from its surroundings. Gas clouds drift through the halo and occasionally fall into the galactic disk. When this gas compresses under gravity, it can trigger new waves of star formation. In certain regions of the disk, giant clouds of gas collapse to form clusters of young stars. These newborn stars illuminate nearby gas clouds, creating glowing nebulae that can be seen across thousands of light years. Meanwhile, older stars eventually reach the end of their lives. Massive stars explode as supernovae, releasing enormous amounts of energy and scattering heavy elements into space. These elements later become part of new stars and planets. Through this cycle of birth and destruction, the Milky Way continues renewing itself. The overall structure of the galaxy also changes slowly as stars move along their orbits. Spiral arms are not permanent features. They are regions where stars and gas become more densely concentrated for a period of time. Over millions of years, stars drift into and out of these arms as they orbit the galactic center. This movement can cause the spiral pattern to shift gradually. The central bar of the galaxy also rotates slowly. As it does, it can influence the flow of gas within the inner regions of the disk. Gas may travel along the bar toward the galactic center, where it can fuel bursts of star formation. These processes reshape the galaxy's appearance over time. Even the warp of the Milky Way's disk may change as gravitational interactions continue. Nearby galaxies, dark matter structures, and tidal forces all contribute to subtle distortions in the disk. These distortions ripple outward like waves across the galaxy. Tracking these changes requires extremely precise measurements. Astronomers must observe stars across the entire sky and measure their motions over many years. Modern surveys such as Gaia have already begun providing this kind of data. The Vera Rubin Observatory will add another important layer to this effort. Because the observatory repeatedly images the sky, it will capture the gradual movements of stars across time. When scientists analyze this enormous data set, they can detect patterns that reveal how the galaxy is evolving. Stellar streams may shift slightly as gravitational forces act upon them. New streams may appear as additional dwarf galaxies are disrupted. The motions of stars in the outer disk may reveal how the warp of the galaxy changes over time. Even the distribution of dark matter may leave subtle signatures in the paths of stars. Over the next decade, these observations will help astronomers refine their models of the Milky Way. The structure of the spiral arms, the shape of the halo, and the distribution of mass throughout the galaxy may become clearer. This research also connects the Milky Way to the broader study of galaxy evolution across the universe. When astronomers observe distant galaxies, they see systems at many different stages of development. Some are small and irregular, others are large spirals like our own galaxy. Some appear to be merging with neighbours, creating complex structures of stars and gas. By studying the Milky Way in detail, scientists gain insight into how galaxies grow and change over time. Our galaxy becomes a laboratory for understanding these cosmic processes, and because we live inside the Milky Way, we can observe its stars far more closely than those in distant galaxies. Every new measurement adds another piece to the story. The map of the galaxy becomes more detailed. The history of its past interactions becomes clearer. The motions of stars reveal how gravity shapes the galaxy's future. Yet despite all of this knowledge, one remarkable fact remains. We are only beginning to see our galaxy clearly. For most of human history, the Milky Way was simply a faint band of light across the sky. Even today, our understanding of its structure continues to evolve as new data becomes available. With telescopes like the Vera Rubin Observatory observing the sky night after night, the picture of our cosmic home is becoming sharper than ever before. For most of human history, the Milky Way was something people simply looked at and wondered about. On clear nights far from city lights, that pale band of stars stretches across the sky like a quiet river. It has always been there, long before telescopes existed, and long before anyone understood what it truly represented. Ancient observers gave it many names and stories. Some imagined it as a heavenly road, others described it as a river in the sky, or a path followed by spirits and gods. These explanations were not attempts to map the universe scientifically. They were ways of making sense of something beautiful and mysterious. The idea that the Milky Way might actually be a vast collection of stars did not arrive until telescopes revealed that the soft glow was made of countless individual points of light. Even then, the larger picture remained unclear. If the Milky Way was made of stars, how big was it? What shape did it form? Where exactly was our solar system located within it? For centuries, these questions remained difficult to answer. The problem was not a lack of curiosity. Astronomers carefully measured the positions of stars, tracked their motions, and built increasingly detailed maps of the sky. But the galaxy itself was simply too large and too complex to understand easily from the inside. We were trying to map a forest while standing among the trees. Because of that, the Milky Way often appeared more like a puzzle than a clear structure. Different observations hinted at spiral arms. Other measurements suggested a central bulge of stars. Radio observations revealed gas clouds stretching across the galaxy, while infrared telescopes uncovered regions hidden behind dust. Each discovery added another piece to the picture. Yet for a long time, the complete image remained just out of reach. Modern astronomy has begun to change that. Over the past few decades, new instruments have provided astronomers with data on an unprecedented scale. Space telescopes such as Gaia have measured the positions and motions of enormous numbers of stars with extraordinary precision. Radio observatories have mapped vast clouds of hydrogen gas across the galaxy. Infrared surveys have revealed stars hidden behind thick dust clouds near the galactic center. When these observations are combined, the structure of the Milky Way becomes clearer. The galaxy appears as a barred spiral system with several arms extending outward through a disk of stars and gas. A central bulge surrounds a supermassive black hole. The disk itself bends slightly at its edges, forming a gentle warp. Beyond the disk lies a halo of ancient stars, globular clusters and stellar streams left behind by smaller galaxies that were gradually absorbed. Surrounding everything is an enormous halo of dark matter, invisible but essential for holding the galaxy together. For the first time in history, astronomers are beginning to see how all of these structures fit together. The Milky Way is no longer just a glowing band in the sky. It is a place with shape, motion, and history. The Vera Rubin Observatory is expected to push this understanding even further. Because the observatory will watch the sky repeatedly for many years, it will collect an enormous archive of observations. Each night of data will add new information about the positions and brightness of stars. Each new observation will help scientists measure stellar motions with greater accuracy. When billions of stars are analysed together, patterns begin to emerge. Spiral arms can be traced with greater precision. Stellar streams become easier to detect. Subtle distortions in the galaxy's disk may reveal how gravitational interactions are shaping the Milky Way. Even the invisible distribution of dark matter may become easier to study through the motions of stars. In many ways, the Rubin Observatory survey will function like a long-term census of the galaxy. Instead of counting individual people in a city, astronomers will be counting and tracking stars across enormous regions of space. The resulting dataset will be one of the largest astronomical archives ever created, and within that archive lies the potential to reveal the Milky Way's structure in greater detail than ever before. Yet beyond the scientific discoveries, there is something quietly meaningful about this effort. For thousands of years, humans could only look at the Milky Way from the outside without knowing what it really was. Now, for the first time, we're beginning to understand the enormous system that surrounds our planet. We know that the Sun travels along an orbit around the galactic centre. We know that our solar system sits within a smaller spiral arm between larger ones. We know that the galaxy itself formed through billions of years of mergers, star formation, and gravitational interactions. And we know that the Milky Way is only one galaxy among hundreds of billions in the observable universe. All of this knowledge has emerged gradually through the work of many generations of astronomers. Each new telescope added another layer of understanding. Each new survey revealed another piece of the galaxy's structure. The Rubin Observatory represents the next step in that process. By observing the sky night after night, it will create a detailed time-lapse record of the universe. Within that record, the motions of stars will reveal the architecture of the Milky Way. Slowly, the scattered lights of the night sky begin to organize themselves into a recognizable structure. A rotating disk of stars, curving spiral arms, a central bar and bulge, a halo filled with ancient stars and the remnants of past galactic encounters. Seeing our galaxy in this way changes how we think about the night sky. Instead of a distant spectacle, the Milky Way becomes something more familiar. It becomes our cosmic home, a vast system of stars through which our solar system travels quietly. Yet even with all of these discoveries, one thing remains certain. There is still much more to learn. The galaxy continues to evolve. Stars continue to form and move. Small galaxies continue to drift through the halo, leaving behind new stellar streams. And as telescopes continue observing the sky, the map of the Milky Way will keep improving. But even now, with all the progress made in recent decades, humanity has reached a remarkable moment. For the first time, we're beginning to see the structure of our own galaxy with real clarity. And understanding that structure offers a new perspective on our place within the universe. Because once we recognize the scale and complexity of the Milky Way, it becomes easier to appreciate just how small our own corner of it truly is. Stepping back for a moment, it is interesting to consider how much our understanding of the Milky Way has changed. Not very long ago, the galaxy was little more than a mysterious glow across the night sky. People could see its soft band of light stretching from one horizon to the other, yet almost nothing about its true nature was understood. The stars seemed scattered across the darkness, without any obvious pattern. And the idea that our Sun might be only one of hundreds of billions of stars inside an enormous rotating galaxy was still waiting to be discovered. Today the situation is very different. Through centuries of careful observation, astronomy has gradually revealed the structure surrounding us. We now know that the Milky Way is a vast barred spiral galaxy filled with stars, gas, dust and dark matter. Its disk stretches roughly 100,000 light-years across, with spiral arms curving outward from a central bar of densely packed stars. At the centre lies a supermassive black hole, surrounded by clusters of stars moving at extraordinary speeds. Beyond the bright disk lies a halo containing ancient stars and globular clusters that orbit far above and below the galactic plane, and surrounding everything is an immense halo of dark matter, invisible but essential for holding the entire system together. This picture of the galaxy did not appear all at once. It emerged piece by piece as telescopes improved and new methods of observation were developed. Each generation of astronomers added another layer of understanding. First came the realization that the Milky Way is made of stars. Later came the discovery that the galaxy contains spiral arms and a central bulge. Radio astronomy revealed the distribution of hydrogen gas across the disk. Infrared observations uncovered stars hidden behind dust clouds near the galactic center. Space missions such as Gaia measured the positions and motions of enormous numbers of stars. And now, observatories like the Vera Rubin Observatory are preparing to watch the sky continuously, building a time-lapse map of the galaxy as it changes. Taken together, these efforts have transformed the Milky Way from a distant curiosity into something more tangible. It is no longer simply a glowing band of light. It is a structured system with a history that stretches back billions of years. Within that system, our solar system occupies a small and relatively quiet location. The Sun orbits the galactic center roughly every 230 million years, travelling through one of the smaller spiral arms between larger ones. During this journey, the solar system passes through regions of interstellar gas and dust, while nearby stars slowly drift along their own orbits. From our perspective on Earth, these motions are almost impossible to notice over short timescales. Yet over millions of years, the positions of stars change and the galaxy evolves. This long journey offers a different way of thinking about the night sky. When we look upward and see the Milky Way stretching across the darkness, we're not observing something distant and separate from us. We are looking outward through the structure that surrounds us. Every star in that glowing band is part of the same galaxy that carries our planet along its orbit. And each of those stars has its own system of planets, gas clouds, and gravitational interactions. The galaxy is not static. Stars form inside giant clouds of gas. Massive stars explode as supernova, spreading heavy elements across space. Small galaxies pass close to the Milky Way and are gradually torn apart by its gravity. Over billions of years, these processes reshape the galaxy's structure. Yet despite all of this activity, the scale of the Milky Way creates an impression of calm. Events that seem dramatic on a local scale often unfold slowly when viewed across the entire galaxy. A stellar stream drifting through the halo may take hundreds of millions of years to complete an orbit. The spiral arms shift gradually as stars move along their paths. Even the future encounter with the Andromeda Galaxy will take billions of years to unfold. Because of these enormous timescales, the galaxy appears steady and unchanging when viewed over the span of a human lifetime. This perspective can feel surprisingly quiet. The Milky Way contains hundreds of billions of stars, yet the distances between them are so vast that most of space remains empty. The nearest star beyond the Sun lies more than 4 light-years away. Even within the crowded spiral arms, stars are separated by distances far greater than the size of planetary systems. From this viewpoint, our cosmic neighbourhood is both immense and spacious. The night sky may appear full of stars, but the galaxy itself is largely made of open space. And within that space, the solar system follows its path around the galactic centre. The Vera Rubin Observatory's long-term survey will continue adding new detail to this picture. By observing the sky night after night, the observatory will measure how stars move and how their brightness changes over time. These observations will help astronomers refine the map of the Milky Way. They may reveal new stellar streams drifting through the halo. They may clarify the shape of the spiral arms or the warp of the galactic disk. They may even provide new clues about the distribution of dark matter that shapes the galaxy's gravitational structure. Each new data set brings us closer to understanding the Milky Way as a complete system. Yet even as the map becomes more precise, the larger perspective remains the same. Our galaxy is vast beyond easy comprehension. The distance from the Sun to the galactic centre is 26,000 light-years. The disk spans roughly 100,000 light-years, and the dark matter halo surrounding the galaxy may extend several times farther than that. Within this enormous structure, the solar system occupies only a tiny fraction of space. Our planet circles an ordinary star in a quiet region of a minor spiral arm. From this location, we observe the galaxy and slowly learn about its structure. The process is ongoing. New telescopes, new surveys, and new discoveries continue expanding our understanding. But even with all the knowledge gained so far, the Milky Way still holds many mysteries. Some stars have not yet been mapped. Some stellar streams remain hidden in the halo. The true nature of dark matter is still unknown, and the future evolution of the galaxy will continue unfolding over billions of years. For now, though, there is something quietly remarkable about the moment we have reached. Humanity has begun to see its own galaxy clearly for the first time. The scattered lights of the night sky have resolved into a vast rotating system with a recognizable structure. Spiral arms curve through the disk. Ancient stars fill the halo. Dark matter forms an invisible framework holding everything together. And somewhere within that immense system, a small star called the Sun carries a tiny planet along its orbit. From the surface of that planet, observers look upward into the night sky and slowly piece together the map of the galaxy they inhabit. It is a long process, built from patience, observation, and curiosity, but step by step the Milky Way is becoming less mysterious. Not because it has grown smaller or simpler, but because we have learned how to see it. And as that understanding continues to deepen, the quiet perspective of our cosmic home becomes a little clearer with every new observation.